Hello there and welcome to Just About Earth, where curiosity can slow down, the lights can stay low, and the largest forces on our planet can be examined without anyone sounding an unnecessary alarm. Tonight, we are looking beneath forests, lakes, towns, roads, and national parks to ask a question that can feel both fascinating and slightly uncomfortable. How long will it be until the next supervolcano erupts? Perhaps you're listening somewhere close to a volcanic landscape, where distant mountains form part of the ordinary view. Maybe the ground beneath you has been geologically quiet for millions of years. Or perhaps you're tucked into bed in a place where the most dramatic thing happening underground is a neighbour trying to assemble furniture at an unreasonable hour. Wherever you are, I would love to know where you're listening from tonight. Is there a volcano anywhere near your part of the world? And before checking a map, did you already know it was there? If you enjoy calm journeys into the workings of our planet, you're very welcome to like the video and subscribe to the channel. It helps this quiet corner of science reach other curious people, including those who enjoy learning about enormous natural disasters immediately before trying to fall asleep. It may not be the traditional route to relaxation, but everyone has a system. Now, get comfortable, let the day settle, and try not to worry about the flaw. For the moment, it is doing exactly what flaws are generally expected to do. The idea of a supervolcano has become one of the most dramatic subjects in popular science. It appears in documentaries, films, online predictions, alarming thumbnails, and conversations that begin with someone saying, "I heard Yellowstone is overdue." That word overdue is usually where the trouble begins. A train can be overdue. A library book can be overdue. A person who promised to fix the leaking tap 3 weekends ago may be very overdue. A volcano, however, does not operate according to an appointment book. It does not count the years since its last major eruption, and gradually become irritated that nobody has prepared a suitable welcome. Volcanic systems are controlled by changing conditions underground. Magma must be generated, stored, moved, and altered. Gas pressure can rise or fall. Rock can fracture, heat can shift through the crust. New magma may enter an old system, or a magma body may cool and become less capable of erupting. Each of these processes can unfold over very different periods, and none of them is required to follow the average interval between ancient eruptions. This means the honest answer to our central question is not a date. Scientists cannot currently tell us that the next super eruption will occur in a particular year, century, or even millennium. They cannot confidently identify which large volcanic system will produce it. They can study the conditions at individual volcanoes, monitor changes, reconstruct past eruptions, and estimate levels of hazard. What they cannot do is start a global countdown. The next super eruption might be many thousands of years away. It could be much farther into the future. A particular caldera that produced an enormous eruption in the past may never produce another eruption of the same size. Meanwhile, a different volcanic system may gradually develop the conditions for a major event. That uncertainty can sound unsettling, but it should not be confused with immediate danger. Uncertainty does not mean that an eruption could happen anywhere without warning tomorrow morning. It means that Earth's largest volcanic events are too rare, too varied, and too dependent on changing geological conditions for us to predict them using a simple repeating timetable. At Yellowstone, probably the best-known volcanic caldera in the world, the US Geological Survey says there is no evidence that a catastrophic eruption is imminent. Its rough estimate of the annual chance of another caldera forming eruption is about 1 in 730,000. But that number comes from averaging only the 2 gaps between Yellowstone's 3 largest ancient eruptions. The scientists themselves warn that this is not enough information for a dependable forecast because catastrophic geological events are neither regular nor predictable. In other words, the calculation is a little like observing that your neighbour replaced a washing machine twice, averaging the dates, and announcing the exact afternoon when the next one will break. You have performed arithmetic, certainly. Whether the washing machine is impressed by it is another matter. This difference between an average and a prediction is essential. Suppose a volcanic region experienced major eruptions 900,000 years apart and then 700,000 years apart. It might be tempting to average those gaps and imagine an 800,000-year cycle, but the apparent pattern could be accidental. The underground system may have changed completely between those events. The next interval could be shorter, longer, or effectively endless if the system no longer develops the necessary magma conditions. Large volcanic systems are not mechanical clocks. They're changing networks of hot rock, partly molten material, gas, groundwater, faults, and crust under stress. Even the word system is useful because it reminds us that we are not dealing with one enormous underground tank waiting to become full. The familiar cartoon version of a supervolcano often shows a gigantic chamber of bright orange liquid beneath a thin roof of rock. The chamber fills steadily, pressure rises, the roof cracks, and disaster follows. Real volcanic plumbing is usually much less tidy. Magma can occupy many connected and disconnected pockets. Much of the material may be crystalline rather than fully liquid. Melt can collect in certain zones, move through fractures, cool, mix with newer magma, release gas, or solidify. A volcanic region can remain active through earthquakes, hot springs, gas release, and changes in the ground without approaching a massive eruption. This is particularly important at Yellowstone because the landscape is visibly restless. Geysers erupt, hot pools change colour, earthquakes occur, sections of ground rise and fall, steam escapes through cracks. To a visitor, it can look as though the entire place is preparing for something. Yet these behaviours are part of Yellowstone's normal activity. As of the US Geological Survey's July 1st, 2026 update, Yellowstone remained at a normal alert level with a green aviation colour code. Scientists reported background seismicity and no significant uplift or subsidence of the caldera or its northern rim since January 2026. A small hydrothermal explosion had occurred in Biscuit Basin in June, but a hydrothermal explosion is driven by hot water flashing into steam and is not the same thing as magma rising toward a supereruption. This does not make hydrothermal explosions harmless. Close to the event, they can throw rocks, hot water, steam, and sediment. They are genuine local hazards, but they do not mean that a continent-scale eruption has begun stretching and warming up beneath the park. A geyser changing its behaviour is not the volcanic equivalent of a warning siren. Sometimes it is simply a geyser changing its behaviour, which is quite enough excitement for one geological feature. Yellowstone receives so much attention, partly because it is well known, closely monitored, and visually impressive. It also has a clear history of enormous eruptions. Its largest known eruption occurred about 2.1 million years ago and produced roughly 2,450 cubic kilometres of volcanic material. Later, large eruptions occurred around 1.3 million and 640,000 years ago, while its more recent eruptions were far smaller lava flows. That history is important, but it does not make Yellowstone the only place worth watching. Large caldera systems exist in New Zealand, Indonesia, Japan, the United States, South America, and other volcanically active regions. Taupō, Toba, Long Valley, Valles Caldera, and several large calderas in Alaska and Asia are part of the broader picture. Each has its own geological history, magma chemistry, crustal setting, and present level of activity. They should not be treated as identical copies of Yellowstone with different scenery. Even the term supervolcano can cause confusion. It sounds like the name of a specific type of mountain, perhaps an ordinary volcano after a particularly successful training program. In practice, many so-called supervolcanoes do not resemble the steep cones people usually imagine. They are often broad caldera systems shaped by the collapse of the ground during an enormous eruption. The label usually refers to a volcanic centre that has produced an eruption at the highest level of the Volcano Explosivity Index, known as VEI8. Such an eruption leaves more than 1,000 cubic kilometres of material. That is an extraordinary volume, but it describes what happened during a past eruption. It does not mean that every future eruption from that location must be equally large. Most eruptions at large caldera systems are smaller, and some activity never produces a magmatic eruption at all. That distinction is often lost when the word supervolcano appears in a headline. A small earthquake swarm beneath a caldera becomes evidence that the giant is waking. A new study of underground magma becomes proof that an eruption is near. A patch of rising ground becomes the beginning of the end. Ordinary observations are placed into the most dramatic possible story, because volcanic system continues behaving like a volcanic system is not considered an especially powerful headline. Scientists look at these signals differently. They do not ask whether one unusual thing happened. They ask whether many measurements are changing together in a way that suggests magma is moving toward the surface. Earthquakes can reveal fractures opening or fluids moving through rock. Satellite measurements and ground instruments can detect swelling or sinking. Gas measurements can show changes in substances released from below. Thermal instruments can identify shifts in heat. Water chemistry may change. None of these signs provides a perfect prediction on its own. An earthquake swarm might result from shifting groundwater. Ground uplift might be caused by fluids moving through the crust. Gas output can vary because of weather and changes in the hydrothermal system. Scientists therefore compare patterns across many instruments and over long periods. The larger the eruption being considered, the more extensive its preparation would probably need to be. According to the US Geological Survey, most scientists expect that the build-up to a catastrophic Yellowstone eruption would be detectable for weeks, and perhaps for months or years. It would probably involve intense earthquake activity and rapid deformation at multiple locations, far beyond ordinary background changes. That does not mean every detail could be predicted, but it does mean a full super eruption is not expected to arrive as a completely silent surprise while everyone is calmly choosing a postcard in the visitor centre. Volcano forecasting is not the same as weather forecasting. Meteorologists can observe a storm moving across an ocean and estimate where it will travel over the next several days. Magma is hidden beneath kilometres of rock, and scientists must interpret indirect signals from the surface. Still, monitoring has improved enormously. Modern volcano observatories use seismometers, satellite radar, global navigation satellite system stations, gas sensors, cameras, thermal equipment, geological surveys and computer models. These instruments allow researchers to notice changes that earlier generations could never have measured. The aim is not always to announce an eruption date. Often the aim is to recognise that unrest has increased, identify the most likely hazards, update alert levels, and help officials make decisions. There is a wide range of possible outcomes between complete quiet and a super eruption. A volcanic system can produce earthquakes without erupting. It can produce a hydrothermal explosion. It can send out a small lava flow. It can create a moderate explosive eruption. It can experience decades of unrest and then settle down again. This is why asking when the next supervolcano will erupt is only the beginning. The question quietly contains several others. What should count as a supervolcano? How often have true super eruptions happened? Which volcanic systems remain capable of producing one? What warning signs would appear? How much warning might we receive? What would the eruption actually do to nearby communities, global aviation, agriculture and climate? And perhaps most importantly, how worried should an ordinary person be? The answers are not all equally dramatic. A super eruption would be a severe global event, but the chance of any specific person experiencing one is extremely low. Smaller eruptions are much more common and can still be devastating. For communities near active volcanoes, preparing for realistic local hazards usually matters far more than focusing only on the largest event physically possible. A person living near a caldera may face danger from ash, earthquakes, landslides, gas, lahars, or hydrothermal activity long before a super eruption becomes relevant. Concentrating entirely on the most extreme scenario can be like preparing for a whale to land on the roof while ignoring the smoke coming from the kitchen. The rarity of super eruptions is difficult for the human mind to handle, because geological time is much larger than personal time. A century feels historical to us. 10,000 years reaches beyond every city, nation, and written record. 1,000,000 years is nearly impossible to picture in ordinary terms, yet a volcanic system may develop, change, erupt, cool, and reactivate across spans of hundreds of thousands or millions of years. From the volcano's point of view, there is no long wait. There are only physical conditions changing at the pace allowed by heat, pressure, rock, and chemistry. The volcano is not sleeping in the human sense, and it is not awake in the human sense. Those are convenient words we use because saying the current measurable state of a complex magmatic and hydrothermal system tends to make casual conversation noticeably less casual. When people say that Yellowstone is overdue, they are usually comparing the time since its last caldera-forming eruption, with an average based on the earlier events. But averages drawn from a few ancient eruptions do not create a schedule. The system that exists today is not identical to the one that existed 640,000 years ago. Researchers continue to study how much melt is present below Yellowstone, where it is distributed, how magma has moved through the crust, and how past eruptions unfolded. The existence of magma beneath a volcanic area is not surprising. Magma is one of the reasons the volcanic area exists. The more useful question is whether enough eruptible magma is accumulating, whether it is moving, whether gases are building pressure, and whether the surrounding rock is responding in ways consistent with an approaching eruption. At present, Yellowstone's monitored behaviour does not indicate an imminent catastrophic event. The US Geological Survey says such an eruption is unlikely in the next few centuries, and that the chance is exceedingly small over the next few thousand years. That assessment may not satisfy anyone hoping for a precise countdown. We're accustomed to exact numbers. We know when an eclipse will occur. We can calculate when a spacecraft will reach another planet. We can predict tides years in advance. It seems reasonable to ask why scientists cannot do the same for a supervolcano. The difference is that eclipses and tides are governed by motions we can measure very accurately, and that repeat in stable ways. A volcanic eruption depends on a changing underground system that we cannot observe directly in full. The necessary conditions may develop unevenly, stop developing, or be altered by processes we have not measured. Scientists can narrow possibilities as unrest increases. They may recognize that an eruption has become more likely. In some cases, they can forecast likely time windows, affected regions, or styles of activity. But forecasting a rare event thousands of years before its preparation begins is not currently possible. There is another difficulty. We have very few true super-eruptions available to study, and most occurred long before scientific instruments existed. Their stories are reconstructed from layers of ash, altered rock, mineral crystals, collapsed calderas, and chemical signatures preserved across wide areas. These records can reveal eruption size, approximate age, magma composition, and sometimes the sequence of events. They cannot provide a complete minute-by-minute account of the warning signs. The most recent eruption recognized by the US Geological Survey as meeting the super-eruption threshold occurred at Taupō in New Zealand about 22,600 years ago. Written records did not exist there, and modern monitoring was still rather a long way from being invented. Humanity therefore has no direct scientific observation of a VEI8 eruption from beginning to end. We understand many of the processes through smaller eruptions, laboratory work, geological evidence, and computer modelling, but there are limits to what the past has preserved. This is not a failure of science. It is simply the nature of studying very rare events. A doctor who has seen thousands of ordinary infections can identify common patterns with great confidence. A geologist studying super-eruptions is working with a small number of events spread across enormous spans of time, with much of the evidence buried, eroded, altered, or scattered across continents. Even identifying the exact size of an ancient eruption can be difficult. Ash may have been carried far away by winds. Deposits may have eroded. Some material may lie beneath oceans, forests, younger lava, or cities whose residents would prefer not to have the entire neighbourhood excavated for scientific completeness. Despite these limits, researchers have built a detailed picture of how large caldera eruptions work. They know that the popular image of a mountain simply exploding is incomplete. They know that huge volumes of magma and gas can produce fast-moving pyroclastic flows, widespread ashfall, and the collapse of land above an emptied or partly emptied magma storage region. They also know that a volcanic centre capable of one enormous eruption can produce many smaller events before or after it. Calling the entire place a supervolcano may encourage us to imagine that it has only two settings: harmless scenery and planetary disaster. Real volcanic behaviour offers a much larger menu, although it is not a menu anyone would be especially pleased to receive. So our journey begins without a ticking clock and without a red circle around a date. There is no known deadline for the next super eruption. There is no evidence that Yellowstone or another famous caldera is currently preparing to produce one. There is also no scientific basis for saying that super eruptions are finished forever. The next one belongs to Earth's future, but its distance from us remains unknown. To understand why that answer is both responsible and useful, we need to look more closely at the event itself. We need to separate the scientific meaning from the dramatic label. Compare a super eruption with the volcanic eruptions people see in ordinary news reports, and examine why a broad depression in the landscape can represent something far larger than a towering cone. That begins with a surprisingly basic question. What exactly makes a volcano super? The word super does a great deal of work here. It makes the volcano sound like a larger, angrier version of an ordinary volcano, perhaps wearing a cape and refusing to respect local planning regulations. But a supervolcano is not a separate species of volcano, and it does not have a special shape that allows us to identify it at a glance. The term refers mainly to the scale of an eruption that a volcanic centre produced in the past. That detail matters. A place is usually called a supervolcano because of something it has already done, not because every eruption it produces is automatically enormous. Yellowstone has experienced very large eruptions, but it has also produced smaller lava flows and explosive events. The same is true of other large caldera systems. Their history may include one or more extraordinary eruptions surrounded by much longer periods of quieter activity and many events that fall far below the supereruption threshold. The standard measurement used in this discussion is the Volcanic Explosivity Index, usually shortened to VEE. It was created to give scientists a practical way to compare explosive eruptions using evidence such as the volume of erupted material, the height of the eruption cloud, the duration of the activity, and observations of how violent it was. It is not measured by one instrument in the way that an earthquake magnitude can be calculated from seismometer recordings. Volcanoes are less considerate and tend to leave scientists with several different kinds of evidence that must be combined. The VEI runs from 0 upward, with the best-known version of the scale ending at 8. A VEI0 event is largely non-explosive. Lava may pour or ooze from a vent without producing a major ash cloud. As the number rises, the amount of explosive material increases greatly. From most steps on the scale to the next, the volume rises by roughly a factor of 10. This means the difference between a VEI5 and a VEI6 is not merely one extra point. A VEI6 eruption may produce around 10 times as much explosive material as a VEI5. A VEI7 may produce around 10 times as much as a VEI6, and a VEI8 is larger again. It is rather like a volume control where each small turn makes the television 10 times louder. You would not get very far before someone in the next town asked you to turn it down. The 1980 eruption of Mount St. Helens is commonly classed as VEI5. It produced roughly 1 cubic kilometre of ash and other explosive material. The 1991 eruption of Mount Pinatubo is an example of VEI6, with a volume near 10 cubic kilometers. A VEI-7 event reaches the region of 100 cubic kilometers. To reach VEI-8, the measured deposits must exceed 1,000 cubic kilometers, or about 240 cubic miles. That is the threshold normally used for a super eruption. 1,000 cubic kilometers is not an easy amount to picture. Most of us do not keep a convenient cubic kilometer in the garden for comparison. A cube measuring 1 kilometer on every side would contain 1 cubic kilometer. Now imagine 1,000 of those cubes. You could arrange them in a block 10 kilometers wide, 10 kilometers long, and 10 kilometers high. The result would be a mass of material extending far above the height at which passenger aircraft normally fly. Another comparison used by the US Geological Survey is that 1,000 cubic kilometers is equivalent to about 400 million Olympic swimming pools, or roughly 400,000 Great Pyramids of Giza. Near the comparison makes the number feel especially normal, but that is because it is not a normal amount of volcanic material. The figure includes material blasted into the atmosphere or swept across the land, including ash, pumice, and other broken volcanic rock. These products are often called tephra. The word covers everything from particles so fine that they can remain suspended in the air to large blocks thrown from the vent. When magma reaches the surface gently enough, it becomes lava and may flow across the ground. During a powerful explosive eruption, the magma is torn apart by expanding gas. It becomes a mixture of fragments, ash, and hot gases moving through the eruption column and across the surrounding landscape. The difference begins partly with the properties of the magma. Some magma is relatively fluid. Gas bubbles can move through it and escape more easily, reducing the pressure available for a violent explosion. This is one reason many Hawaiian eruptions produce flowing lava rather than towering columns of ash. Other magma is thick and resistant to movement. Gas cannot escape as readily, so pressure can build. When the surrounding rock breaks or the magma reaches the surface, the expanding gas can fragment it with tremendous force. Large caldera-forming eruptions are commonly associated with silica-rich magma, such as rhyolite, which tends to be more viscous than basaltic magma. Viscosity is simply a measure of how easily a substance flows. Water has low viscosity. Cold syrup has higher viscosity. Rhyolitic magma has no intention of behaving like either one, but the syrup comparison at least moves us in the correct direction. Temperature, crystal content, chemical composition, dissolved water, carbon dioxide and other gases all influence how magma behaves. A reservoir may contain areas with different amounts of liquid melt and solid crystals. Fresh magma may enter from below, adding heat and gas. Older magma may cool against the surrounding rock. Different batches may mix. A super eruption therefore requires more than a large quantity of hot material somewhere underground. The system must develop a very large amount of magma that is capable of erupting. It must contain enough liquid melt, gas and pressure, and it must connect with pathways that allow material to reach the surface. Not every large magma body will erupt. Some cool underground and eventually become solid rock. Others feed many smaller eruptions. A system may remain active for hundreds of thousands of years, while never again producing an event as large as the one that gave it the supervolcano label. This is one reason the label can be misleading. It encourages us to imagine that a supervolcano is constantly holding 1,000 cubic kilometers of liquid magma beneath a fragile lid. In reality, magma storage zones can be broad, layered, partly crystalline, and divided among connected pockets. They are often described as mush systems because much of their volume may consist of crystals surrounded by smaller amounts of melt. Mush is not the most threatening word in the English language. It sounds more like breakfast than a geological hazard. Unfortunately, volcanic mush can become very important when heat, new magma and gas alter its condition. A large explosive eruption may begin when magma rises through fractures and pressure is released. As magma moves upward, The pressure pressing down on it decreases. Dissolved gases begin to form bubbles, rather as gas appears when a bottle of fizzy drink is opened. The similarity ends before anyone attempts to shake a volcano and hand it to a friend. Inside rising magma, the gas bubbles can expand rapidly. If the magma is too sticky to let them escape, the pressure breaks the magma into fragments. Those fragments, together with hot gas, can be driven upward in a high eruption column. The column may carry ash high into the atmosphere. Larger pieces fall closer to the vent, while fine ash can travel hundreds or thousands of kilometers, depending on wind, particle size, and the duration of the eruption. An eruption column does not always remain stable. If it becomes too dense to rise, it can collapse. The mixture of hot gas, ash, pumice, and rock then rushes outward along the ground as a pyroclastic density current. These currents are among the most dangerous volcanic processes. They can move quickly, remain extremely hot, cross ridges, fill valleys, and bury large areas. The deposits left behind by major currents can harden into rock called ignimbrite. During an exceptionally large eruption, pyroclastic currents may spread across enormous distances around the volcanic centre. Repeated currents can lay down thick sheets of volcanic material over the landscape. Later, erosion may cut through those deposits, allowing geologists to study separate layers and reconstruct parts of the eruption. As magma leaves the underground storage region, the rock above it loses support. Cracks can form in a broad ring around the surface. Blocks of crust may begin to sink, sometimes in stages and sometimes through a series of large collapses. This collapse produces a caldera. A caldera is a large depression formed when the surface drops after magma is withdrawn from below. It is not simply a very large crater created by an explosion. Some explosive excavation may occur, but the defining process is collapse. Imagine removing part of the support beneath the roof of a building. The roof does not need to be blasted into the sky to create a hole. It may sink or fall into the space below. A collapsing volcanic system is vastly more complicated, but the basic idea is similar, with the small difference that the roof may be tens of kilometers across and the building inspector is unlikely to attend. Very large calderas can be difficult to recognize from the ground. We often imagine volcanoes as steep mountains with smoking summits, but a caldera may be so broad that a person can stand inside it without seeing the entire boundary. Forests, lakes, roads, towns, and younger volcanic features can occupy the depression. Yellowstone caldera is roughly 70 kilometers long and 45 kilometers wide. It does not look like a single cone because it is not one. Its landscape contains plateaus, lakes, valleys, thermal areas, lava flows, and the remains of overlapping volcanic structures. Lake Taupō in New Zealand occupies part of another large caldera system. Toba in Indonesia contains an enormous caldera lake with an island rising within it. Long Valley in California appears as a broad basin near the eastern Sierra Nevada. These places do not look identical because calderas evolve after they form. Lakes may fill them. New magma can push parts of the floor upward. Later lava flows and small cones can appear inside or along their edges. Rivers and glaciers reshape the terrain. Sediment accumulates. Plants grow. People arrive and build roads, houses, farms and cafes, because humanity has never seen an interesting geological hazard without eventually opening somewhere to buy coffee nearby. The presence of a caldera does not automatically mean a super eruption occurred. Calderas form across a wide range of eruption sizes. Kilauea in Hawaii experienced major summit collapse during its 2018 eruption after magma drained from beneath the summit, but that event was nowhere near VE8. Calderas are produced by collapse. The word does not specify that the eruption crossed the super eruption threshold. The reverse distinction is also useful. When scientists use the word super eruption, they are describing the event. When popular accounts use supervolcano, they are describing the volcanic centre associated with such an event. Some volcanologists prefer to avoid the word supervolcano because it gives the impression that these systems form a neat scientific category. They do not suddenly become different objects when an eruption passes 1,000 cubic kilometers. The threshold is useful for comparison, but nature does not pause at 999 cubic kilometers and announce that the eruption is still officially ordinary. A VEI-7 eruption can also have severe regional or global effects. The difference between a very large VEI-7 and a smaller VEI-8 may be less important to people experiencing it than the label suggests. Both can produce widespread ash, destructive pyroclastic currents, major disruption, and effects on the atmosphere. The scale itself has limitations. Eruptions are assigned VEI values by combining several kinds of evidence, and those kinds do not always agree. A very high eruption plume might suggest one value, while the total ash volume suggests another. Duration matters too. An eruption that releases material gradually over years is not equivalent to one that sends a similar amount into the atmosphere over a few hours. The scale mainly measures explosive behaviour. It is not a complete measure of danger, damage, or human suffering. A modest eruption close to a densely populated city can be more deadly than a much larger eruption in a remote region. Weather conditions can direct ash toward communities or away from them. Heavy rain can mix with ash to create lahars. Snow and ice can melt. Aviation routes can be disrupted. Buildings may collapse under the weight of wet ash. Population, preparation, communication, infrastructure, and the timing of evacuation all affect the outcome. A VEI number tells us something important about the eruption, but it does not tell the whole story. This is similar to knowing the size of a storm without knowing where it will make landfall. The number is useful, but it would be unwise to stop asking questions. Estimating the VEI of an ancient eruption is especially difficult. No one was present with satellites, weather radar, cameras, and notebooks when the largest known super-eruptions occurred. Geologists must work backward from the deposits. They map layers of ash and ignimbrite. They measure thickness and area. They identify crystals and compare chemical signatures. A thin ash layer discovered far away may be matched with deposits near the original caldera. By combining these pieces, researchers estimate how much material was produced. Much of the evidence may be missing. Wind and water erode deposits. Rivers move them. Glaciers scrape them away. Forests and soil cover them. Younger eruptions bury them. Some ash falls into the ocean, where locating and measuring it becomes considerably less convenient. Pumice also contains many gas bubbles, so a deposit may occupy more space than the original dense magma did underground. Ash can be compacted after it lands. Pyroclastic deposits may have different densities in different places. Scientists must decide exactly what kind of volume they are comparing. For these reasons, eruption volumes are estimates, and estimates can change as new fieldwork is completed. An eruption near the VEI-8 boundary might be moved above or below it. That does not mean the earlier science was dishonest. It means ancient eruptions do not arrive with receipts. The largest known Yellowstone eruption occurred about 2.1 million years ago and produced an estimated 2,450 cubic kilometers of material. A later caldera-forming eruption, roughly 631,000 years ago, also reached VEI-8. Taupō's Oroanui eruption, about 25,500 calendar years ago, produced deposits exceeding the 1,000 cubic kilometer threshold and is generally described as the most recent super-eruption. Even these enormous events may be more complicated than a single uninterrupted blast. Geological research suggests that some deposits assigned to one Great Yellowstone eruption may have formed during several eruptive phases, possibly with substantial pauses between them. Scientists continue to investigate whether certain events treated as single VEI-8 eruptions were actually groups of smaller but still immense eruptions, separated by years or even decades. This matters because the popular image of a super eruption is usually one sudden explosion. The real event might unfold through a sequence of escalating eruptions, pauses, vent openings, column collapses, and caldera subsidence. Different sections of the ring fracture system might become active at different times. The landscape could change throughout the sequence. No VEI8 eruption has been scientifically observed with modern instruments, so researchers cannot say exactly how long one would last. Estimates based on deposits suggest that much of the material in some cases may have erupted over hours or days, but separate phases could extend the wider episode. This uncertainty also affects the question of warning. If a super eruption requires the mobilization and eruption of an enormous magma volume, it is reasonable to expect significant unrest beforehand. But the first eruption in a sequence might not immediately reveal the final total size. Scientists could detect rising earthquake activity, ground deformation, gas changes, and magma movement without knowing at once whether the system would produce a moderate eruption, a large eruption, or something far greater. The eventual VRZE is partly an account of what the eruption did, not a label that can always be attached before it begins. There is no underground gauge with a needle moving from perfectly fine through rather concerning and finally into a red area marked super. Volcano observatories must interpret multiple measurements while the system changes. Another common misunderstanding is that the size of a volcano above ground determines the size of its eruption. A tall cone can produce a dangerous eruption, but height alone does not reveal the volume of magma stored in the crust. Large caldera systems may have no central mountain at all. Mountains are built by material accumulating around vents. Calderas are created when ground collapses. One rises above the surrounding landscape, the other may be expressed as a broad depression. A super eruption is therefore associated less with the impressive height of a mountain and more with the scale and behaviour of the underground magmatic system. Nor is every eruption from a large caldera explosive. After a caldera forming a vent, thick lava may rise slowly and spread inside the depression. Domes can form, smaller vents may open. At Yellowstone, many later eruptions produced rhyolite lava flows rather than another caldera-forming catastrophe. A volcanic system can spend most of its active life doing things that do not match its dramatic reputation. That does not make monitoring unnecessary. A history of enormous eruptions is scientifically important, and even smaller activity can threaten nearby communities. It simply means the word super should not overpower all the other information. What makes an eruption super, then, is principally its enormous volume of explosive deposits, more than 1,000 cubic kilometres, corresponding to VEI8. Such an event commonly releases huge ash clouds and pyroclastic currents, and may remove enough magma from beneath the surface to form a large caldera. What makes a volcanic centre a supervolcano is that it produced an event of that scale at some point in its history. The label does not tell us when it will erupt again. It does not guarantee that its next eruption will be large. It does not mean a vast lake of fully liquid magma is waiting beneath the surface. It does not mean every earthquake or steaming pool is a sign of disaster. It tells us that under particular conditions, at a particular time in the geological past, that system was capable of releasing an extraordinary amount of material. Those conditions are rare. Building a large silicic magma system can require long periods of magma supply, heating, cooling, crystallization, mixing and storage. The crust must accommodate the material. Enough eruptible magma must become connected. Pressure and gas must develop. A route to the surface must open. Many volcanic regions begin parts of this process without reaching the final result. Some systems produce repeated moderate eruptions that release magma before a much larger body can collect. Others cool. Tectonic conditions change. The supply from deep in the earth weakens or shifts. A famous supervolcano may therefore be less likely to produce the next super eruption than a system receiving far less public attention. Past size matters, but present conditions matter too. That leaves us with a planet containing several large calderas, each with its own history and its own underground structure. Some are visibly active, with earthquakes, hot springs, gas release and moving ground. Others appear quiet at the surface while still preserving evidence of enormous ancient events. To understand where the next supereruption might eventually occur, we need to move beyond the most famous name on the map. Yellowstone is only one member of a much larger family, and the other sleeping giants beneath our feet have stories that are just as important. That larger family is spread across several continents, although its members do not all behave in the same way. Some contain lakes, some sit beneath national parks, some lie beside major cities. A few show obvious signs of activity, while others have remained quiet for so long that their volcanic origins are easy to overlook. Grouping them together as sleeping giants is convenient, but it can also be misleading. They are not all sleeping, and they are not all equally likely to produce another enormous eruption. Volcanologists usually describe a volcano as active when it has erupted during a geologically recent period, or still shows evidence that its underground system is functioning. This evidence might include earthquakes, moving ground, volcanic gas, hot springs, or young magma beneath the surface. Dormant is often used for a volcano that is not erupting now, but could erupt again. Extinct suggests that its magma supply has ended, and another eruption is not expected. Those categories sound clear until an actual volcano is placed inside them. A volcanic system can remain quiet for tens of thousands of years and then reactivate. Another can produce earthquakes and hot springs for centuries without releasing magma at the surface. A third may contain lingering heat, but no realistic path toward a future eruption. The boundary between dormant and extinct is therefore not marked by a helpful sign saying, "No further eruptions beyond this point." The problem becomes even greater at large calderas because their lives can be extremely long. A caldera-forming eruption may be followed by lava flows, smaller explosive eruptions, uplift, subsidence, hydrothermal activity, and long quiet intervals. Activity may move from one section of the system to another. A new volcano can grow inside the old caldera. The original magma body may cool while a different batch of magma rises nearby. The giant eruption is only one event in a much longer history. Yellowstone provides the most familiar example. Its modern caldera stretches roughly 85 kilometers by 45 kilometers across part of Yellowstone National Park. The region experienced 3 major caldera-forming eruptions during the past 2.1 million years, although only the oldest and youngest meet the usual 1,000 cubic kilometer threshold for a super eruption. The middle event, which formed the Henry's Fork caldera, was enormous by ordinary standards but considerably smaller than the other two. USGS.gov. This is worth remembering because people often speak of Yellowstone as though it has produced 3 identical explosions on a regular cycle. It has not. The events differed greatly in size, occurred at different locations, and formed parts of a volcanic field that shifted across the region over time. Yellowstone's activity is linked to a long volcanic track across the Snake River Plain. As the North American tectonic plate moved, the location of the most intense volcanism changed, leaving a chain of older volcanic centres extending for more than 700 kilometres southwest of modern Yellowstone. At least 6 earlier centres along this track produced large caldera-forming eruptions before activity became concentrated beneath the present plateau. USGS.gov https://www.usgs.gov/volcanoes/yellowstone/summary-yellowstone-eruption-history. The landscape seen today is not simply the crater from one blast. It is the combined result of repeated eruptions, ground collapse, lava flows, uplift, faulting, glacial erosion, rivers, and hydrothermal activity. The caldera has been partly filled by later rhyolite flows, some more than 100 meters thick. Smaller basaltic eruptions occurred around its margins, and hydrothermal explosions have continued during the current geological period. usgs.gov/volcanoes/Yellowstone/science/geology-history-Yellowstone. More than 10,000 hot springs, geysers, mud pots and steam vents occupy the Yellowstone region. Their heat comes from the volcanic system, but they belong mainly to its hydrothermal plumbing. Rain and melted snow seep underground, encounter hot rock, and return toward the surface as heated water or steam. Old Faithful is therefore not a small exhaust pipe connected directly to a vat of eruptible magma. It is part of a complicated water system driven by heat from below. This is reassuring, although standing beside boiling water that erupts according to its own schedule can still make a person respect the plumbing. The ground at Yellowstone also rises and falls. Earthquake swarms occur regularly. These movements may be linked to magma, hydrothermal fluids, regional faults, or a combination of processes. They show that Yellowstone is active, but active does not mean ready to produce a super eruption. Since the most recent caldera-forming eruption, about 631,000 years ago, Yellowstone has produced around 80 smaller eruptions. Many were lava flows rather than major explosive events, and the most recent magmatic eruption occurred about 70,000 years ago. The system has therefore done a great deal since its last super eruption without repeating that event. Sustery usgs.gov https://www.usgs.gov/volcanoes/questions-about-Yellowstone-volcanic-history. A future Yellowstone eruption, should one occur, would be far more likely to resemble one of those smaller events than its largest ancient explosions. Even then, smaller is a geological description. A lava flow or moderate explosive eruption inside a national park would still create serious local problems and a particularly difficult morning for anyone responsible for road closures. Far across the Pacific, the central North Island of New Zealand contains another major concentration of large caldera volcanoes. The Taupō volcanic zone extends for hundreds of kilometres and exists because the Pacific plate is being forced beneath part of the Australian plate. This tectonic process generates magma and stretches the crust, allowing volcanic systems to develop across the region. The zone includes familiar cone volcanoes such as Ruapehu and Tongariro, but it also contains calderas that are much broader and less obvious. 8 caldera volcanoes lie in the central part of the zone, including Taupō and Okataina, 2 systems that have been exceptionally productive. gns.cri.nz https://www.ns.c/r-science/natural-hazards-risks/volcanoes/volcano-types/. Lake Taupō fills much of the caldera created during the Orowanui eruption, about 25,500 years ago. That event is generally identified as the most recent eruption to exceed the super-eruption threshold. It released well over 1,000 cubic kilometres of material through several eruptive phases, altered the landscape of the central North Island, and left a basin now occupied by New Zealand's largest lake by surface area. gns.cri.nz https://www.gns.cri.nz/r-science/land-dynamics/kermadec-arc-and-volcanic-zone/. A large lake can make a caldera seem quiet and complete, as though the eruption happened. The hole filled with water, and geology moved on to another project. Taupō has not behaved that way. The volcano has erupted 29 times during the past 30,000 years. Only 3 of those eruptions were very large. The other 26 were smaller events that formed lava domes or spread ash and pumice over parts of the surrounding region. Its most recent eruption occurred about 1,800 years ago, and although smaller than Orowanui, was one of the most violent eruptions anywhere in the world during the past 5,000 years. gns.cri.nz https://www.gns.cri.nz/r-science/natural-hazards-new-zealands-volcanoes/. This history demonstrates an important rule. A system capable of a super eruption spends most of its eruptive life not producing super eruptions. Taupō may generate unrest without erupting. It may eventually produce a moderate event. It may produce another very large eruption at some unknown point in the future. Its history does not allow anyone to select one of those outcomes in advance simply by counting the years. Okataina, northeast of Taupō, adds another complication. It is a large volcanic centre made from several overlapping structures, lava domes and vents rather than one simple crater. Its most recent major activity was the 1886 eruption of Mount Tarawera, which opened a 17-kilometre-long fissure and killed more than 100 people. That eruption was not a super eruption, but it occurred within a region known for producing immense volumes of rheolitic magma over geological time. gns.cri.nz Taupō and Okataina are useful reminders that the place producing frequent small or moderate eruptions may deserve more immediate attention than the place famous for one ancient giant event. Emergency planning must deal with what is plausible during a human lifetime, not only with a maximum eruption preserved in the rocks. To the northwest, on the Indonesian island of Sumatra, Lake Toba occupies an even larger volcanic depression. The Toba caldera is approximately 100 kilometres long and 35 kilometres wide. It formed through 4 major explosive episodes beginning more than 1 million years ago, with the latest and largest taking place around 74,000 years ago. volcano.sa.edu https://volcano.si.edu/volcano.c fm $lang equals en &vn equals 261090. The young Toba tuff eruption was among the largest known eruptions of the Quaternary period. Its ash deposits have been identified across a vast area, and enormous pyroclastic flows covered the region around the vent. The collapse left a caldera that later filled with water, while part of its floor rose to form Samosir Island. Samosir is not a small island floating casually in the middle of the lake. It is a large uplifted block of volcanic deposits, evidence that the caldera floor moved after the Great Eruption. Villages, fields, roads, and holiday accommodation now occupy parts of a structure created by post-eruption resurgence. Toba is often presented as a volcano that nearly ended humanity. The claim is linked to the idea that volcanic cooling caused a severe reduction in the human population. The eruption undoubtedly affected climate and environments, but the scale of its impact on early humans remains debated. Genetic evidence, archaeological findings, and climate models do not support one simple story in which nearly everyone disappeared at exactly the same time. The uncertainty is important because dramatic versions of Toba's history are sometimes treated as established fact. Scientists agree that the eruption was enormous. They do not all agree that it created a single global human bottleneck of the kind often described in documentaries. Toba's current appearance also shows why old calderas are difficult to classify. The Smithsonian's Global Volcanism program lists its last known eruption broadly within the Pleistocene, but the wider complex contains post-caldera lava domes, geothermal activity, and younger volcanic features whose ages are not all firmly established. volcano.si.edu https://volcano.volcano.cfm $lang equals en &vn equals 261090. That does not provide evidence that another Toba super eruption is approaching. It means that a caldera can continue changing long after its largest event, and that an absence of recent recorded eruptions does not automatically settle every question about the system beneath it. Indonesia contains many active volcanoes and lies along a major subduction zone, so its monitoring agencies must divide attention across numerous hazards that are more immediate than a repeat of the young Toba tuff. Volcanoes that erupt every few years naturally demand more daily attention than one whose greatest known event occurred before written history. California contains another large caldera east of the Sierra Nevada. Long Valley formed about 760,000 years ago during the Bishop Tuff eruption. The depression is roughly 32 kilometers long and 16 kilometers wide, and the town of Mammoth Lake sits close to its southwestern edge. USGS.gov. The caldera did not stop evolving after the Bishop Tuff was deposited. Its central floor rose to form a resurgent dome. Later eruptions occurred around its margins and along the connected Mono-Inyo volcanic chain. The broader region contains lava domes, craters, young flows, hot springs, faults, and Mammoth Mountain, which is itself a younger volcanic feature. Long Valley became a major scientific concern in 1980 after a series of strong earthquakes and the discovery that part of the caldera floor had risen. Further earthquake swarms and uplift occurred during the following decades. Carbon dioxide released from beneath Mammoth Mountain killed trees in several areas, showing that gas was moving through the ground even though no eruption followed. USGS.gov, https://www.usgs.gov/publications/calfornias-restless-giant-long-valley-caldera. The unrest created understandable concern. Roads, ski areas, homes and businesses occupy the region, and California already has considerable experience with geological events arriving at inconvenient moments. What happened next was not a straightforward march toward an eruption. Activity rose and fell. Some earthquake swarms were intense, then ended. Uplift slowed or changed. Gas continued to escape in certain areas. The system remained active without crossing into an eruption. Long Valley, therefore, gives scientists something valuable, a modern record of caldera unrest that did not immediately produce magma at the surface. It shows how difficult it can be to separate a temporary disturbance from the beginning of a genuine eruptive sequence. USGS assessments state that future eruptions in the wider Long Valley monolake region are most likely to resemble the smaller events that have occurred during the past several thousand years, not a repeat of the Bishop Tuff supereruption. The next vent could also open outside the main caldera, particularly along the Mono-Inyo chain. USGS.gov. This means that even knowing the location of an ancient caldera does not reveal exactly where the next eruption will begin. Magma follows weaknesses in the crust, and those weaknesses can extend well beyond the most obvious depression on a map. Farther southeast, in New Mexico, Valles Caldera forms a broad, grass-covered basin in the Yemas Mountains. Its present landscape includes forested hills, streams, meadows, wildlife, and a large central resurgent dome. To someone arriving without geological information, it may look like an unusually wide mountain valley. Valles experienced two major caldera-forming eruptions. The younger occurred about 1.25 million years ago and created much of the present depression. Lava domes continued to form around the caldera afterward, with the most recent eruption occurring around 40,000 years ago. The USGS currently classifies its threat potential as moderate rather than high or very high. USGS.gov, https://www.usgs.gov/volcanoes/valleys-caldera. That rating does not mean the past eruption was unimportant. It reflects a broader assessment that includes the volcano's activity, the kinds of eruptions expected, nearby populations, infrastructure, and the ability to monitor it. Volcanic threat is not a competition based only on who produced the largest ancient deposit. This becomes particularly clear in Italy, where Campi Flegrei lies partly beneath the western side of Naples and the town of Pozzuoli. Its name means the burning fields, which is an admirably direct piece of local branding. Campi Flegrei is a 13-kilometre wide caldera containing craters, fumaroles, hot ground, urban districts, archaeological sites, roads, and densely populated neighbourhoods. It formed through large explosive eruptions, including the Campanian ignimbrite around 36 to 39,000 years ago, and the Neapolitan yellow tuff around 15,000 years ago. Its most recent eruption, Monte Nuovo, occurred in 1538 and built a new cone over several days. volcano.si.edu, https://volcano.si.edu/volcano.cfm ?VN equals 211010. Campi Flegrei is often called a supervolcano in popular accounts, although its known eruption volumes do not clearly place it in the same VER8 category as the Orua Nui eruption, or Yellowstone's largest events. It is still one of the world's most closely watched calderas because millions of people live nearby and because it has undergone repeated periods of uplift and earthquakes. The ground around Pozzuoli has risen and fallen for centuries through a process called bradyseism. During major episodes in the 20th century, uplift damaged buildings and forced evacuations. A new phase of uplift began in 2005 and has been accompanied by increasing seismic activity, changes in gas, and continued concern among residents. In July 2026, Italy's National Institute of Geophysics and Volcanology was still addressing public questions about carbon dioxide and ongoing bradyseismic activity in the area. Its statement stressed that gas concentrations and volcanic processes must be judged through measurements rather than rumours or assumptions based on unrelated events such as the length of a railway closure. INGV.IT. Campi Flegrei demonstrates why eruption size is not the only reason a volcano matters. Even a moderate eruption in a crowded metropolitan area could create a major emergency. The most realistic future eruption might be far smaller than the caldera-forming events preserved in the landscape, yet still require the movement of large numbers of people. Japan offers another version of the same problem. Era caldera occupies the northern part of Kagoshima Bay on the island of Kyushu. The caldera formed during a major explosive eruption around 22,000 years ago. On its southern edge stands Sakurajima, a younger volcano that began growing about 13,000 years ago. Sakurajima is not sleeping. It is one of Japan's most active volcanoes and regularly produces ash-bearing explosions. Kagoshima City lies only a short distance across the bay, and residents are accustomed to ash forecasts, cleaning routines, and restrictions near the crater. During July 2026, eruptive activity was continuing at Sakurajima's Minamidake crater. This ordinary activity was not evidence that the entire Era system was entering a caldera-forming eruption. It was activity from a frequently erupting cone located within a much larger volcanic structure. volcano.si.edu, https://volcano.si.edu/volcano.cfm ? lang equals en &vn equals 2828080. Era shows that a large caldera can contain a smaller volcano with its own active plumbing. The underground systems may interact, but an eruption from the cone should not automatically be interpreted as the beginning of the largest possible event. The same principle applies elsewhere. Rabaul in Papua New Guinea contains active vents within a flooded caldera. Large calderas exist in Alaska, the Andes, the Kamchatka Peninsula, and other parts of the Western Pacific. Some produced eruptions approaching or exceeding 100 cubic kilometers. A few may have produced larger events whose deposits remain incompletely mapped. There are also ancient super-eruption sites that are no longer considered likely candidates for another event. The La Garita caldera in Colorado produced the enormous Fish Canyon tuff roughly 28 million years ago. But that does not make modern Colorado the most likely location of the next super-eruption. The tectonic and magmatic conditions that created it have changed. This is why a list of the largest eruptions in geological history is not the same as a list of present volcanic threats. A useful assessment must consider whether magma is still being supplied, whether the crust remains warm, whether earthquakes and deformation are occurring when younger eruptions took place, what kind of magma was involved, and how the regional tectonic setting has changed. Even with that information, no observatory can rank the world's calderas and announce which one will erupt next. Their timescales overlap poorly with human records, and many parts of the world do not have equally dense monitoring networks. Some systems are covered by hundreds of instruments. Others are observed by a smaller number of seismic stations and occasional satellite passes. A remote caldera may show few recorded earthquakes because it is quiet, or because the nearest instrument is too far away to detect the smallest events. An absence of data and an absence of activity are not always the same thing. The giants beneath our feet are therefore a mixed group. Yellowstone has a famous hydrothermal system and a long history of smaller post-caldera eruptions. Taupō has erupted repeatedly since its super eruption. Toba preserves one of the largest calderas on Earth, but has a less complete recent record. Long Valley has demonstrated decades of unrest without erupting. Campi Flegrei places a restless caldera beside millions of people. Ira contains a volcano that is already erupting regularly without producing a giant caldera event. None of these systems is known to be preparing for a super eruption. That statement does not mean they are ignored. It means their ordinary earthquakes, gas emissions, ground movements, and thermal changes have to be measured carefully enough that ordinary behaviour can be separated from something new. Before scientists can recognise an awakening, they must first learn how each volcano behaves while it is not erupting. That requires instruments sensitive enough to detect the movement of a few millimetres, earthquakes too small for people to feel, changes in gases that cannot be seen, and heat travelling through rock kilometres below the surface. The giants do not provide spoken announcements, so scientists have built several different ways to listen. Listening to a volcano begins with learning its ordinary background noise. Every active volcanic system has its own habits. Some produce frequent small earthquakes. Some swell and sink slowly. Some release large amounts of gas through open vents, while others hide most of their activity beneath lakes, forests, ice, or city streets. A signal that would be unusual at one volcano may be completely normal at another. This is why scientists cannot place a standard alarm beside every caldera and wait for the same needle to move. They first need a baseline, a long record showing how the system behaves during quiet periods, seasonal changes, storms, earthquake swarms, and episodes of unrest that do not end in eruption. The task is similar to listening to a house at night. Pipes click, floorboards shift, a refrigerator hums, wind moves around the windows. Once you know those sounds, you're less likely to mistake the heating system for an intruder. Volcano observatories do something similar, although their houses are several kilometres deep and contain molten rock. The most familiar instruments are seismometers. These detect vibrations travelling through the ground. Large earthquakes can be recorded across the world, but volcano monitoring often depends on events so small that nobody nearby feels them. Sensitive instruments can detect tiny fractures opening, faults slipping, fluids moving, and pressure changing beneath the surface. When magma pushes through rock, it can create earthquakes. The surrounding crust does not open politely, it cracks in stages, producing repeated seismic signals that may trace the movement of magma toward the surface. A cluster of earthquakes occurring within a limited area and period is called an earthquake swarm. Swarms are common in volcanic regions, especially around calderas with active faults and hydrothermal systems. They can last for hours, days, weeks, or longer. Or the number of earthquakes matters, but location and depth are often more useful. If earthquakes begin deep beneath a volcano and gradually appear at shallower levels, scientists may consider whether magma or gas is rising. If they migrate sideways, fluids may be moving through a fracture. If they remain along a known fault, ordinary tectonic stress may be responsible. The character of each signal also provides clues. Volcanotectonic earthquakes resemble ordinary fault earthquakes. They occur when brittle rock breaks. Long-period earthquakes have lower frequency vibrations and are often linked to the movement of gas or liquid through cracks. Volcanic tremor is a more continuous vibration that can be produced by sustained fluid movement, magma rising through a conduit, or an eruption already in progress. None of these signals automatically means that a large eruption is coming. A volcano may produce thousands of earthquakes and then settle down. Magma can rise into the crust, stall, cool, or spread sideways without reaching the surface. Water heated by the volcanic system can move through cracks and generate intense seismic activity. Regional faults can also produce earthquake swarms near a caldera by coincidence or through shared stress. This is why scientists do not simply count earthquakes and begin loading evacuation buses when the total reaches a particular number. They examine whether the earthquakes are becoming more frequent, larger, shallower, or concentrated beneath a likely vent. They compare the activity with previous swarms. They check whether the ground is deforming at the same time. They look for gas changes, rising heat, altered springs, and other measurements that might support the interpretation. A single signal can be interesting. Several independent signals changing together are much more significant. Ground deformation is one of the clearest ways to detect pressure changing underground. When magma or volcanic fluids enter a storage region, they can push the surrounding rock outward. The surface may rise, tilt, or spread apart. If material drains away or pressure falls, the ground may sink. These movements are often small. A person standing on the surface would not notice the landscape rising by a few centimetres over several months. Fortunately, modern instruments are better at noticing centimetres than people are. Global Navigation Satellite System stations, often called GPS stations in everyday conversation, can measure the position of fixed points on the ground with remarkable precision. A receiver mounted firmly to bedrock communicates with satellites and records whether the station has moved upward, downward, or sideways. A network of stations around a volcanic system can reveal the shape of the deformation. If several stations move away from one central area, pressure may be increasing below it. If only one side moves, the source may be offset or magma may be travelling along a sloping intrusion. Tilt meters provide another close view of movement. They measure tiny changes in the angle of the ground. A good tilt meter can detect changes far smaller than anything a person could feel, including the slight lifting or lowering of a volcano's slope as pressure changes beneath it. The basic idea is straightforward. Place an instrument on the ground, record its angle, and watch for movement. The engineering becomes less straightforward when the instrument must survive snow, rain, lightning, animals, unstable soil, and visitors who are curious about boxes with cables. Satellite radar has expanded this work enormously. A method called interferometric synthetic aperture radar, usually shortened to INSAR, compares radar images collected from space at different times. Small changes in the distance between the satellite and the ground produce coloured patterns that reveal uplift or subsidence across wide areas. INSAR is especially valuable at large calderas because deformation may extend across tens of kilometres. A few ground stations can provide very precise measurements at selected points, while satellites show the wider shape of the movement. The two methods work well together. Ground instruments provide continuous local records. Satellites cover broad regions, including places that are difficult or dangerous to reach. Even then, deformation is not a simple eruption switch. Calderas can rise and fall for reasons that do not lead to an eruption. Magma may enter a deep reservoir and stop. Hot water and gas may pressurize a hydrothermal system. Seasonal snow, rainfall, groundwater changes, or the weight of a lake can cause small surface movements. Tectonic faults may also shift the land. Yellowstone has experienced repeated episodes of uplift and subsidence. Long Valley has risen during periods of unrest. Campi Flegrei has moved upward and downward over centuries. These changes show that pressure is being redistributed underground, but they do not tell scientists by themselves whether eruptible magma is moving toward the surface. To understand the source, researchers model the deformation. They ask what size, shape, depth, and pressure change could produce the pattern seen at the surface. A simple model might treat the source as an expanding sphere. This is useful for an early estimate, even though magma chambers rarely resemble perfect balloons. More detailed models may include sheets of magma, vertical cracks, horizontal layers, faults, and zones of hot deformable rock. Models are not photographs of the underground system, they are tested explanations. Several different sources can sometimes produce similar surface patterns, so the result must be compared with earthquakes, gas, geology, and other evidence. Gas is another major part of the conversation between a volcano and the surface. Magma contains dissolved gases, including water vapour, carbon dioxide, sulfur dioxide, hydrogen sulfide, and smaller amounts of other compounds. Deep underground, high pressure keeps much of this gas dissolved in the magma. As magma rises and pressure decreases, gas begins to separate into bubbles. The timing depends on the gas. Carbon dioxide tends to separate from magma at greater depth than sulfur dioxide. Changes in the amount or ratio of these gases can therefore offer clues about what is happening underground. Scientists collect gas directly from fumaroles, vents, and hot springs. They may carry portable instruments across volcanic ground, install permanent sensors, fly aircraft through plumes, or use equipment mounted on drones. Satellites can detect large sulfur dioxide clouds from space. Direct sampling can involve standing near hot, acidic gases while wearing protective equipment and holding a collection tube in exactly the right place. It is serious scientific work, although it can look from a distance like someone trying to interview steam. An increase in sulfur dioxide may suggest that magma has moved to a shallower level where the gas can escape. A rise in carbon dioxide across the soil can indicate deeper degassing. Changes in gas chemistry may also show that magma is interacting with groundwater or heating the hydrothermal system. Yet gas measurements are affected by many ordinary conditions. Wind can dilute or redirect a plume. Rain may dissolve gases. Snow can block vents. Groundwater can absorb sulfur compounds before they reach the surface. A sealed volcanic system may trap gas even while pressure rises below, meaning a low measurement is not always reassuring. At some volcanoes, an open conduit releases gas continuously. At others, most of the gas passes through soil or springs. Scientists need to understand the local pathways before deciding whether a change is important. Thermal monitoring adds information about heat. Satellite sensors can detect warm ground, hot crater lakes, lava, and newly opened vents. Ground cameras can record heat that human eyes cannot see. Instruments placed in wells or springs can measure changing water temperatures. A growing thermal area might indicate that hot gas or fluid is moving closer to the surface. A crater lake may warm as volcanic heat increases. Snow or ice may melt in unusual patterns. Heat can also change for non-volcanic reasons. Sunlight warms exposed rock. Rain cools the ground. Seasonal snow cover alters satellite measurements. A hot spring may change because a channel becomes blocked, rather than because magma is rising. Hydrothermal systems make interpretation especially difficult. Water circulating above a magma body can store and move large amounts of heat. Pressure can build in pockets of hot water and steam, creating explosions without magma reaching the surface. These explosions may occur with little warning because the final trigger can involve a local blockage or sudden pressure change. Monitoring a hydrothermal explosion is not the same as monitoring a supereruption, although both occur within the same broad volcanic environment. Scientists also watch water chemistry. Hot springs, wells, crater lakes, and streams can carry dissolved minerals and gases from underground. Changes in acidity, chloride, sulfur compounds, or other chemical markers may show that the pathways of hot fluids have shifted. Again, local knowledge matters. A spring may change after heavy rainfall. An earthquake can open one crack and close another. Sediment can block a channel. Animals, vegetation, and human activity can affect samples. No volcano sends a pure message. Every measurement arrives mixed with weather, geology, equipment limits, and background activity. Gravity measurements provide another way to investigate hidden changes. Gravity varies slightly, depending on the amount and density of material beneath an instrument. If magma enters a region or groundwater moves through the crust, the local gravitational field can change by a tiny amount. These changes are far too small to make anyone feel lighter while walking across a caldera. They require sensitive gravimeters and careful correction for elevation, tides, atmospheric pressure, and other influences. When gravity increases while the ground rises, scientists may infer that dense material has entered the system. If the ground rises without the expected gravity change, gas or low-density fluids might be involved. The interpretation is not always unique, but it helps narrow the possibilities. Electrical and magnetic methods allow researchers to examine how well underground rocks conduct electricity. Hot rock, magma, salty water, and hydrothermal fluids can conduct electricity differently from cold, dry rock. Magnetotelluric surveys measure natural variations in Earth's electric and magnetic fields. From those measurements, scientists can build three-dimensional images of electrical conductivity beneath a volcano. These images do not show bright orange magma in the way a medical scan might show a bone. They reveal regions whose electrical properties are consistent with melt, hot fluids, altered rock, or combinations of those materials. Seismic tomography works in a related way using earthquake waves. Seismic waves travel at different speeds through different types of rock. They may slow down in hot or partly molten regions and move faster through colder, denser rock. By recording waves from many earthquakes at many stations, scientists can estimate the underground structure. The process resembles a medical scan in principle, but the patient is part of Earth's crust and does not remain conveniently inside a machine. Tomography has transformed our understanding of large volcanic systems. Instead of one simple chamber, many appear to contain broad regions of hot, partly molten rock with smaller areas of higher melt concentration. The word molten can be misleading here. A region that slows seismic waves may contain only a fraction of liquid melt. The rest can be solid crystals and rock. Scientists must combine seismic results with laboratory experiments and other measurements before estimating how much eruptible magma is present. Researchers also study magnetic changes, infrasound, and acoustic signals. Infrasound consists of sound waves below the normal range of human hearing. Explosions, gas jets, rockfalls, and eruptions can create pressure waves that travel through the atmosphere. Arrays of specialized microphones can detect these signals at great distances. At a volcano with frequent explosions, infrasound can help identify an event when clouds or darkness hide the summit. It can also distinguish an explosion from an earthquake occurring underground. Cameras provide a simpler but essential form of monitoring. Time-lapse images show changes in vents, domes, glaciers, crater lakes, and plumes. High-resolution satellite photographs allow scientists to map new cracks, landslides, and deposits. Drones now reach places that would be too dangerous for field teams. They can carry gas sensors, cameras, thermal instruments, and mapping equipment. A drone lost inside a crater is unfortunate. A scientist lost inside a crater is considerably more so. Much of volcano monitoring depends on instruments, but rocks collected in the field provide a longer record than any electronic network. Minerals grow inside magma before an eruption. As conditions change, they form layers that preserve information about temperature, pressure, chemical composition, and interactions between different magma batches. A crystal can contain a record of fresh magma entering a reservoir, heating older material, and beginning the sequence that ended in eruption. Scientists analyze these layers using microscopes, chemical instruments, and diffusion models. This work can estimate how much time passed between a change in the magma system and the eruption. At some volcanoes, fresh magma arrived days or weeks before the surface activity. At others, changes began months or years earlier. These results are sometimes called crystal clocks. The name is convenient, although no crystal contains tiny hands pointing toward the next eruption. Crystal clocks describe past events. They help scientists understand which processes have triggered eruptions before. If monitoring later detects similar processes, those past examples may improve forecasting. Old deposits also show how the volcano has behaved across thousands of years. Geologists dig trenches, examine cliffs, drill cores, and map ash layers. They determine which areas were covered by pyroclastic currents, how far ash travelled, where lava flowed, and how often eruptions occurred. This information becomes the basis for hazard maps. A hazard map does not predict the exact route of a future eruption. It shows areas that could be affected by particular processes based on geology, terrain, and models. Valleys may guide lahars and pyroclastic currents. Prevailing winds may make some regions more likely to receive ash. Low ground may collect water and sediment. Past vents may mark weaknesses where future activity could occur, though new vents can also open elsewhere. Observatories bring all of this information into one place. Seismologists study earthquakes. Geodesists examine deformation. Geochemists track gases and water. Geologists compare the activity with ancient deposits. Remote sensing specialists analyze satellites and thermal data. Emergency managers consider roads, hospitals, communication, and evacuation. No single person sits in front of one flashing screen and decides whether a supervolcano is awake. Teams review the evidence, discuss alternative explanations, and update alert levels when the overall pattern changes. Different countries use different systems, but most have stages representing normal activity, unrest, increasing concern, and eruption. An alert level is not a measure of eruption size. A volcano can move to a high alert because a small eruption is imminent. A caldera can remain at a low alert even though its distant past includes a super eruption. The purpose is to describe present behaviour, not historical reputation. False alarms are unavoidable. Scientists may detect magma moving upward, issue warnings, and then watch the intrusion stop. This does not mean the warning was wrong. The hazard genuinely increased, but the system changed before erupting. Volcanoes do not make promises after they begin showing unrest. The opposite problem is also possible. An eruption may develop faster than expected. Some small eruptions begin after only short warning, particularly at systems with open pathways or limited monitoring. A super eruption would involve such a vast amount of magma that scientists generally expect extensive and unmistakable unrest beforehand. Earthquake activity would likely increase dramatically. Ground deformation could become rapid and widespread. Gas and heat might change across several areas. The pattern would probably continue evolving rather than appearing as one isolated swarm. That does not mean scientists would immediately know the eruption's eventual size. The early warning signs of a small eruption and the early stages of a much larger event may overlap. Magma moving upward produces earthquakes whether it later erupts 1 cubic kilometre or 1,000. The final scale depends on how much magma becomes connected, how the underground system responds, whether the roof begins collapsing, and whether the eruption continues opening new pathways. During the first stages of unrest, scientists might confidently say that the probability of an eruption had increased without being able to say exactly what kind of eruption would follow. This is one of the hardest parts of volcanic communication. People often want a simple answer, yes or no, safe or dangerous, erupting or not erupting. Scientific forecasts usually come as probabilities that change with new data. a volcano may have a 10% chance of erupting within a certain period. If it does not erupt, the forecast was not necessarily a failure. A 10% chance means that no eruption was still the more likely outcome. Weather forecasts face the same misunderstanding. When a forecast gives a 30% chance of rain and the day remains dry, the atmosphere has not exposed meteorology as an elaborate fraud. The less likely outcome simply did not happen. At a large caldera, the consequences of warning decisions are substantial. Evacuating a major population costs money, disrupts lives, affects hospitals, closes schools, and can place vulnerable people at risk. Waiting too long can be worse. Scientists and officials must act before certainty exists, because certainty may arrive only after the eruption has begun. Continuous monitoring reduces this uncertainty, but it cannot remove it. The strongest forecasts come from convergence. Earthquakes move upward. The ground inflates rapidly. Gas chemistry changes. Heat increases. The pattern fits known magma pathways. These signals continue and intensify. Each new piece supports the same explanation. If the signals disagree, scientists have to consider other possibilities. Earthquakes without deformation may come from fault movement. Deformation without gas may involve deep magma that is not rising. Gas changes without seismicity may be caused by hydrothermal circulation. The instruments are not listening for one dramatic roar. They are listening for relationships. A volcano awakening from a long quiet period would probably not do so with a single sign. Its underground system would begin changing pressure, breaking rock, moving fluids, releasing gas, and disturbing the surface. Those changes would appear in several kinds of data, sometimes gradually, and sometimes in sudden bursts. The challenge is deciding how those signals alter the chance of an eruption. Scientists are becoming better at that task. Monitoring networks are denser, satellites pass more frequently, computer models are faster. Laboratory experiments reproduce magma conditions with greater precision. International observatories share data and lessons from eruptions around the world. Machine learning methods can search large seismic records for patterns that human analysts might miss, although they still require careful testing. A computer trained on one volcano may not understand another, because each system has different plumbing, rocks, noise, and behaviour. Even the most advanced algorithm can struggle when the volcano refuses to resemble its training data. The future of forecasting will probably come from combining improved instruments with better physical models, not from one magical detector. Scientists may never predict eruptions with the exactness of an eclipse. They can still identify rising unrest, estimate likely scenarios, and provide enough warning for practical decisions. At well-monitored volcanoes, those abilities have already saved lives. For a possible super-eruption, the monitoring task would begin long before anyone used that word publicly. Early unrest might look like many other episodes that eventually faded. Only as the changes spread, intensified, and involved larger parts of the system would the more extreme possibilities become harder to dismiss. The instruments would tell scientists that the volcano was changing. Geological history would show what it had been capable of before. Models would estimate where magma was moving and which hazards could follow. The question would then shift from whether anyone was listening to whether the signals could reveal what the system intended to do next. And that is where observation becomes forecasting, with all the uncertainty that comes with trying to predict an eruption that may not occur for thousands of years. Forecasting begins by accepting a slightly frustrating fact. Detecting change is not the same as knowing how that change will end. Scientists may observe earthquakes beneath a caldera, measure rising ground, and find new gas moving through the soil. Those observations can show that something is happening underground. They cannot always reveal whether the activity will fade, produce a small eruption, or continue towards something much larger. This is why volcanologists usually speak of forecasts rather than predictions. In ordinary conversation, the words sound almost identical. In science, they can carry different expectations. A prediction often sounds exact. The volcano will erupt at this time from this location with this amount of material. A forecast is more cautious. It describes the likelihood of several possible outcomes over a stated period. A weather forecast might say that rain is likely tomorrow afternoon. It usually does not promise that the first drop will land on a particular garden chair at 3:17. Volcano forecasts work in a similar way, except that the clouds are hidden beneath several kilometers of rock and may remain there for another 10,000 years. Scientists try to answer several separate questions. Is an eruption becoming more likely? When might it begin? Where could a vent open? How large could the event become? What hazards would appear first? How long might the activity continue? These questions do not become answerable at the same moment. A monitoring network may detect magma rising and give reasonable confidence that an eruption is possible within days or weeks. The location of the earthquakes and deformation might suggest where the magma is heading. Its eventual size, however, could remain uncertain until the eruption is underway. This uncertainty is especially important when discussing supereruptions. A supereruption is defined by the total amount of material released. Scientists cannot measure that total until the event has progressed, and the early signals may resemble those of a much smaller eruption. The movement of magma creates earthquakes whether the magma later produces a modest lava dome or begins a caldera-forming sequence. Expanding gas affects pressure in both cases. The ground may rise above a small intrusion as well as a much larger one. What matters is how much magma becomes connected, how quickly it moves, how much gas it contains, and whether the surrounding crust begins to fail across a broad area. The first signs would therefore not arrive carrying a label marked VEI8. A volcano observatory might initially report increased unrest. If earthquakes intensified, deformation accelerated and gas measurements changed, the alert level could rise. Scientists would update their assessment as new information arrived. The forecast might begin with several branches. No eruption occurs. A small eruption opens from one vent. A larger explosive eruption develops. Activity spreads across the volcanic system. Each branch would be assigned a probability based on monitoring, geological history, models, and expert judgment. These branching diagrams are called event trees. The trunk represents the present situation. Each split represents a question. Will unrest continue? Will magma reach the surface? Will the eruption become explosive? Will it remain near one vent? Or will it involve a larger part of the system? The numbers are not permanent. If the ground stops moving and the earthquakes decline, the no eruption branch becomes more likely. If magma rises rapidly and several sections of the caldera begin deforming, more serious branches gain weight. Event trees allow scientists to express uncertainty without pretending that all outcomes are equally likely. They are also useful after an eruption begins because volcanic activity can change style, location, and intensity. An eruption may pause and restart. A lava-producing vent may become explosive, a new vent can open. Forecasting continues throughout the crisis rather than ending when the first material reaches the surface. For the next supereruption, however, there is currently no active crisis to place into such a tree. No monitored caldera is showing evidence that a VEI8 eruption is approaching. There are restless volcanic systems, but unrest is common and does not by itself indicate that 1,000 cubic kilometers of material is preparing to leave the crust. Long-term estimates must therefore rely heavily on the geological record. Scientists identify ancient supereruption deposits, date them, estimate their volumes, and compare their spacing through time. From this record, they can calculate an average global frequency. The difficulty is that the record is incomplete. Large eruptions leave enormous deposits, so they are more likely to survive than small ones. Even so, millions of years of erosion, burial, tectonic movement, ocean sedimentation, and later volcanism can hide or destroy evidence. Some supereruptions may remain undiscovered beneath the sea or under younger rock. Dating also carries uncertainty. A deposit may be confidently placed near a certain age while its exact date remains uncertain by hundreds or thousands of years. That is excellent precision for deep geological history, but less helpful when someone asks whether an eruption is likely before next Tuesday. Published estimates of the average interval between global supereruptions vary considerably. Older studies suggested figures near 50,000 years, while other work has suggested intervals of 100,000 years or longer. Analyses that attempt to correct for missing deposits have sometimes produced shorter estimates, including a return period near 17,000 years for magnitude 8 eruptions, but with very wide confidence limits. Researchers caution that the small number of known events and the incomplete record make these figures uncertain. An average global interval is not a countdown. Suppose, for illustration, that an event occurs on average once every 50,000 years. That does not mean Earth waits 50,000 years between eruptions. Two could occur relatively close together, followed by a gap much longer than the average. The number also combines many unrelated volcanic systems. An eruption in New Zealand does not reset a timer beneath Indonesia. Yellowstone does not become safer because a caldera erupts somewhere else. Nor does it become more dangerous because the global average has supposedly been exceeded. A global recurrence estimate is useful for broad-risk studies. It can help governments and researchers compare super-eruptions with asteroid impacts, pandemics, and other rare global hazards. It cannot identify the next location or year. Trying to predict one particular caldera from its past intervals is even harder. Yellowstone's 3 best-known caldera-forming eruptions occurred about 2.08 million, 1.3 million, and 631,000 years ago. That gives only 2 intervals, roughly 780,000 and 669,000 years. Averaging them produces a figure close to 725,000 years. This is the source of the repeated claim that Yellowstone erupts every 600,000 or 700,000 years. It's also a good example of how a correct calculation can support an incorrect conclusion. 2 intervals are not enough to establish a reliable cycle. The eruptions were different sizes and occurred in a volcanic system that shifted and changed over time. Most systems known to have produced one super eruption have not produced several, and systems with repeated giant eruptions do not show perfectly regular spacing. Yellowstone is therefore not overdue, and there is no requirement that it ever produce another caldera-forming eruption. The frequently quoted annual probability of a Yellowstone caldera-forming eruption is about 1 in 730,000, or roughly 0.00014%. That number is obtained by turning the average interval into an annual rate. It can be useful for placing the hazard in perspective, but it should not be treated as a precise forecast. The estimate assumes that the long-term average applies equally every year, and that the volcanic system remains capable of the same event. Neither assumption is guaranteed. A lottery with a fixed set of numbered balls has stable rules. A volcano changes while we observe it. Magma supply can strengthen or weaken. Underground reservoirs grow, cool, crystallize, or drain. Tectonic stresses shift. A pathway that existed during an ancient eruption may now be sealed. The probability this year may therefore differ from a simple geological average, particularly when present monitoring shows no evidence of an approaching eruption. The US Geological Survey describes the 1 in 730,000 figure as a rough approximation based on too few intervals for a critical judgment. It also states that there is no evidence of an imminent catastrophic eruption at Yellowstone, and that such an event is unlikely during the next few centuries. Scientists can make a separate estimate for any volcanic eruption at Yellowstone, including much smaller events. Using the history of lava flows and eruptions rather than only the Great Caldera collapses produces an annual probability on the order of 0.001%. Even that estimate may overstate the immediate likelihood because the monitored system is not currently showing signs of an impending magmatic eruption. These numbers answer different questions, which is why combining them carelessly creates confusion. The chance of some volcanic activity is not the chance of a supereruption. The chance of a hydrothermal explosion is not the chance of magma reaching the surface. The chance of a lava flow is not the chance of a continent-wide ash disaster. It is rather like asking about the probability of experiencing weather and being given only the probability of a hurricane. Both involve the atmosphere, but one is slightly more common during an average week. A more physical approach asks whether the underground system currently contains the ingredients needed for a super eruption. Researchers use seismic imaging, electrical surveys, mineral studies, and models to estimate the size and condition of magma storage regions. At Yellowstone, these studies reveal large zones containing hot, partly molten material. The word large attracts attention, but the phrase partly molten matters just as much. Much of the region is crystal rich and not immediately eruptible. Earlier USGS summaries estimated the shallow rheolitic reservoir at roughly 5 to 15% melt, with most of the remaining material solid but hot. More recent imaging methods continue to refine the structure and may identify areas with greater melt concentration, yet finding melt beneath an active volcanic field is not evidence that it is ready to erupt. For a super eruption, a large volume of melt would probably need to become connected and mobile. Fresh magma might enter from below, supplying heat and gas. Crystal-rich zones could partially remelt. Pressure could increase. Fractures might link previously separated pockets. These changes could take long periods to develop. Some may occur gradually over thousands of years. The final movement toward eruption, however, could be much faster. Minerals preserved in ancient deposits suggest that magma systems can remain in a largely stored or crystalline condition for long periods and then become activated before eruption. Fresh magma may disturb the reservoir, alter its chemistry, and trigger movement over timescales ranging from years to months or even shorter periods. This creates two different forecasting problems. The first asks whether a volcanic system could produce another giant eruption during its geological future. That question may involve hundreds of thousands of years and cannot be answered precisely. The second asks whether a system showing major unrest is likely to erupt soon. Once strong signals begin, scientists may be able to provide useful forecasts over days, weeks, months, or years. For a catastrophic Yellowstone eruption, most specialists expect the build-up to be detectable for weeks, and perhaps months to years. Strong earthquake swarms and rapid deformation would likely occur at levels far above the normal background. Because a very large part of the system would need to become involved, intense unrest would probably appear at several locations rather than as one ordinary cluster of small earthquakes. That expectation is reassuring, but it's not a guarantee of a comfortable timetable. Detectable does not mean immediately understood. Scientists might notice major changes without knowing at first whether the result would be a lava flow, a moderate explosive eruption, or something larger. Warning time is also different from decision time. Officials might need to close roads, move residents, protect water supplies, and reroute aircraft before the scientific picture becomes clear. Waiting for complete certainty would remove the value of the warning. At the same time, announcing the possibility of a super eruption too early could cause panic, economic disruption, and distrust if the activity later declined. People might refuse a later evacuation because the earlier crisis ended quietly. This is why scientific language during unrest can sound restrained. Phrases such as increased probability, possible magmatic intrusion, and several scenarios remain under consideration may seem unsatisfying, but they communicate what the measurements actually support. A calm sentence can describe a serious situation. A dramatic sentence can describe very little. The location of the next super eruption may be even harder to forecast than its time. Past super eruption sites attract attention because they have already demonstrated the required capacity. Yellowstone, Taupō, and Toba naturally remain part of the discussion. Yet a system does not need to have produced a recognized VEI8 eruption before developing one in the future. A large magma system may be forming beneath a region whose earlier deposits have not been fully mapped. Another may lie beneath an oceanic area where evidence is difficult to recover. A caldera known mainly for VEI6 or VEI7 eruptions could, under different conditions, produce something larger. Scientists can identify regions where tectonic conditions favour large silicic magma systems. Subduction zones, continental volcanic provinces, and areas of prolonged crustal melting receive particular attention. That narrows the search from the entire planet to several broad belts, which is useful but not quite the same as circling one volcano on a map. There are about 1,350 potentially active volcanoes on land, not including the continuous volcanic systems along the ocean floor. Only a small fraction are large calderas, and fewer still have a known history of super eruption. Monitoring quality varies greatly among them. A famous volcano with a dense network may appear more restless simply because scientists can detect its smallest movements. A remote caldera with only a few instruments might look quiet because its whispers are not being recorded. Satellites are reducing this imbalance. Radar can detect ground deformation across isolated regions. Thermal instruments can identify new heat. Atmospheric sensors can find sulfur dioxide. Global earthquake networks record larger events even where local stations are sparse. Still, satellites cannot provide every measurement. They may pass only at certain intervals. Clouds interfere with some sensors. Thick vegetation, snow, water, and rapid surface changes can make deformation harder to interpret. Gas may never reach the atmosphere in amounts large enough to detect from orbit. The ideal system combines satellites with instruments on the ground, geological mapping, local observations, and scientists familiar with the volcano's normal behaviour. Improving the global network may be one of the most practical ways to reduce uncertainty about the next large eruption. It cannot tell us today which volcano will produce a super eruption 10,000 years from now. It can make it less likely that serious unrest develops unnoticed. Computer models are also becoming more capable. Researchers simulate magma entering the crust, heating older rock, forming reservoirs, and placing stress on the surface. Models suggest that magma supply rate, buoyancy, crustal strength, and the timing of repeated injections can influence eruption size. Smaller eruptions may be triggered mainly by pressure from new magma, while very large events may require a large buoyant magma body capable of overcoming the surrounding crust. These models help explain why super eruptions are rare. A volcanic system must receive magma under suitable conditions for long enough to build an enormous reservoir without repeatedly releasing most of it through smaller eruptions. It is a difficult balance. If magma arrives too slowly, it may cool and solidify. If it escapes too easily, frequent eruptions prevent a giant volume from accumulating. If the crust allows magma to spread into many disconnected zones, the system may never gather enough mobile material in one connected body. The conditions must be inconveniently specific, which is fortunate for everyone living above them. Models remain simplified versions of natural systems. The exact shape of a reservoir is uncertain. Rock strength changes with temperature and pressure. Fluids move through fractures too small to map. Chemical reactions alter the magma over time. A model can show what is physically possible and identify measurements that would support one scenario. It cannot yet take a few quiet decades of data and announce the next super eruption date. Machine learning may improve the detection of patterns in large monitoring records. Algorithms can classify earthquakes, recognize subtle tremor, compare deformation sequences, and search for combinations that preceded earlier eruptions. The limitation is the shortage of examples. A system designed to recognize cats can be trained using millions of cat photographs. A system designed to recognize the final approach to a super eruption has no modern examples at all. Researchers can train algorithms on smaller eruptions and episodes of caldera unrest. But a super eruption may involve processes that have never appeared together in an instrument record. The computer may become excellent at recognizing familiar behavior, while remaining uncertain when presented with something genuinely new. Artificial intelligence will probably help scientists process information. It is less likely to replace the need for field geology, physical models, and human judgment. Even ordinary eruption forecasting remains difficult. Some volcanoes show clear warning for months. Others accelerate rapidly. Some produce major unrest and then stop. Scientists have made substantial progress, but eruption onset is still forecast with uncertainty, and undetected precursors remain possible, especially where monitoring is limited. A super-eruption would probably produce stronger and broader warning than a small event, yet its rarity gives scientists fewer opportunities to learn how that warning would unfold. There may be no single stage at which a normal volcanic crisis suddenly becomes recognizable as a future super-eruption. The evidence could build progressively. At first, deep earthquakes might suggest fresh magma entering the system. Years later, deformation could show pressure increasing in several reservoirs. Gas release might spread. Shallow earthquakes could intensify. Sections of the caldera might begin moving rapidly. An initial eruption could then release pressure and end the crisis. It might continue as a moderate event. Alternatively, it could destabilize more of the reservoir, widen fractures, and begin caldera collapse. Forecasts would change throughout this sequence. Early estimates might favor a small eruption. Later evidence could make a larger outcome more plausible. The most extreme scenario might not become likely until the activity was already severe. This is not because scientists failed to see the volcano. It is because the volcano's future would not be fully decided by its first movement. Complex systems can cross thresholds. A crack opens, changing pressure elsewhere. Gas escapes, causing magma to rise faster. Part of the roof sinks, pushing magma toward new fractures. One process alters the conditions controlling the next. The final size may depend on this chain of events, not only on the volume present before the eruption began. So can we predict the next super-eruption? Not in the form people usually imagine. We cannot name the volcano, select a date, and begin a reliable countdown. Global recurrence estimates are too broad. Individual eruption intervals are too irregular. The geological record is too incomplete, and the underground systems continue changing. We can identify volcanic regions capable of very large eruptions. We can study how their magma systems are organized. We can estimate long-term probabilities, though those estimates carry wide uncertainty. We can monitor earthquakes, deformation, gases, heat, gravity, and water. If a large system begins moving toward eruption, we can expect increasing signs that should improve short-term forecasts. The answer therefore changes with distance. Thousands of years beforehand, prediction is extremely weak. Months or years beforehand, major unrest could become visible. Days or weeks beforehand, scientists might provide increasingly urgent forecasts, although the final eruption size could still be uncertain. There is no clock telling us how long remains. There is a planet being watched more closely than ever before. That leaves another question hiding behind the prediction problem. If scientists did detect a large caldera moving toward eruption, what exactly would they be warning us about? The phrase super-eruption suggests one enormous explosion, but the real event would involve several hazards arriving across different distances and times, from the collapse of land near the caldera to ash travelling across countries and atmospheric effects continuing long after the ground became quiet. The first effects would not wait for the eruption to reach its greatest size. By the time scientists seriously considered a super-eruption possible, the surrounding region would probably already be experiencing strong earthquakes, rapid changes in the ground, damaged roads, disrupted utilities, closed airspace, and large evacuations. The event would begin as a developing emergency rather than one sudden explosion appearing without context. Exactly what followed would depend on the volcano. A super-eruption at Yellowstone would not unfold in precisely the same way as one at Taupō, Toba, or another large caldera. The shape of the underground magma system, the surrounding terrain, the magma's gas content, the location of opening vents, the weather, and the speed of caldera collapse would all affect the outcome. There is no single standard super eruption waiting in a geological instruction manual. Still, past deposits show a general sequence of hazards that could occur. Magma would rise through fractures, pressure would fall, and dissolved gases would expand. The magma could break apart into ash, pumice, and larger fragments, creating powerful explosive columns above one or more vents. These columns might rise tens of kilometers into the atmosphere. Lightning could flash inside them as ash particles collided and built electrical charges. Daylight near the volcano would fade behind thick clouds of ash. The sound would not resemble one clean bang. It could involve repeated explosions, continuous roaring, earthquakes, thunder, collapsing ground, and the movement of enormous volumes of material. Anyone close enough to watch the full sequence would already be much too close. During some large eruptions, the rising column becomes too dense to remain supported by hot air and gas. It collapses, sending pyroclastic density currents away from the vent. These currents are fast-moving mixtures of ash, volcanic fragments, and extremely hot gas. They travel close to the ground, often following valleys, but sometimes crossing ridges and other obstacles. In major caldera-forming eruptions, they can spread across areas extending many tens of kilometers from the source. The currents would be the most immediately destructive hazard near the volcano. Buildings, forests, vehicles, power lines, and almost everything else in their path could be buried, burned, broken, or carried away. The safest response would not involve sheltering behind a sturdy table. It would involve having left the area before the currents began. Around Yellowstone, the US Geological Survey states that areas closest to the caldera in parts of Wyoming, Montana, and Idaho could be affected by pyroclastic flows during another giant caldera-forming eruption. The exact area would depend on the eruption, but the nearest region would face conditions that ordinary emergency response could not operate within. The deposits from ancient super-eruptions reveal how far these currents can travel. They may fill valleys with layers of hot ash and pumice hundreds of meters thick. Some remain hot enough after deposition for the fragments to weld together, eventually forming solid ignimbrite. An ignimbrite sheet can cover thousands of square kilometers. Long after the eruption, it may look like a broad plateau or a sequence of cliffs. Without geological training, a person could walk across one and have no reason to suspect that the entire landscape was once buried by a single eruptive episode. Near the source, several vents might open across a wide region, rather than at one central crater. Cracks could form around the developing caldera. Lava fountains, ash columns, and ground collapse might occur at different locations as pressure shifted underground. As more magma escaped, the unsupported crust above the storage region could begin to sink. The collapse might happen through enormous blocks dropping along ring-shaped faults. It could proceed in stages, with sections of the surface descending during separate pulses. This process would force additional magma out of the system, rather like pressing down on a container, although few containers are 80 kilometers wide and filled with material hot enough to melt rock. Caldera collapse can make an eruption larger by creating new fractures and allowing more magma to escape. The eruption removes support, the roof sinks, the sinking roof pushes more magma outward, and the process continues. The surface would not necessarily fall into one simple bowl. Parts could tilt, break apart, or remain as blocks surrounded by collapsed ground. Later activity might raise sections again as new magma entered below, but that would belong to a much longer recovery measured in centuries or millennia. For people living farther away, the main immediate hazard would be ash. Volcanic ash is not soft material from a fireplace. It consists of tiny pieces of volcanic glass, minerals, and rock. The particles can be sharp, abrasive, and difficult to remove. Fine ash can remain suspended in the atmosphere and travel great distances, while heavier material falls closer to the volcano. Wind would control the direction of the ash cloud, but a super eruption could continue long enough to encounter changing winds at different altitudes. Instead of producing one narrow trail, it might spread ash across several directions over time. Computer models of a possible Yellowstone super eruption suggest that a broad part of North America could receive ash, with the thickest deposits nearer the volcanic centre. Past Yellowstone eruptions left identifiable ash across much of the western half of the continent. The amount would decrease with distance, but even thin deposits could disrupt modern systems far from the caldera. Ashfall close to the volcano could accumulate rapidly. Roofs would become a major concern, especially if rain or snow made the ash wet. Wet ash is much heavier than dry ash, and flat or weak roofs could collapse under the load. Removing it would be difficult because ash does not simply disappear when swept from one surface. It has to be moved somewhere. Clearing a roof transfers it to the ground. Clearing the road transfers it to a storage site. Wind can then lift the dry material and spread it again. After smaller eruptions, communities have spent months or years dealing with remobilized ash. Vehicles and footsteps disturb it. Storms wash it into drains and rivers. Agricultural work lifts it into the air. A super eruption would create the same problems across a much larger area. Breathing fine ash can irritate the eyes, throat, and lungs. People with asthma or other respiratory conditions would be especially vulnerable. Well-fitting masks and indoor filtration would reduce exposure, but those supplies would be difficult to distribute if roads, airports and power systems were already disrupted. Ash can enter buildings through small gaps. It settles into machinery, ventilation ducts, computers, electrical equipment, and food storage areas. It can scratch glass and painted surfaces. Ordinary cleaning methods may send it back into the air, allowing a room to be cleaned several times with very little sense of achievement. Water systems would face several problems. Ash falling into reservoirs could increase sediment and alter water quality. Pumps and filters might clog. Electricity failures could stop treatment facilities. Demand would rise because cleaning ash requires water, precisely when water utilities would prefer that everyone use less. Wastewater systems could also become blocked if large amounts of ash entered drains. Rainfall might carry ash from streets into sewers and treatment plants. A city receiving only a few centimetres could face a complicated infrastructure emergency, even if no buildings were directly destroyed. Electrical networks are vulnerable because wet ash can conduct electricity. Deposits on insulators may cause short circuits and flashovers. Ash can contaminate substations, reduce the efficiency of power plants and damage generators. Repair crews would have difficulty reaching failed equipment if roads were covered, visibility was poor and vehicles were breaking down. Restoring one part of the network would not help much if ash immediately caused another failure. Telecommunications would probably become overloaded as millions of people tried to contact relatives, check official updates, or upload dramatic photographs of a sky that everyone had already noticed was unusual. Physical damage and loss of power could interrupt mobile towers, internet services, radio transmitters, and data centers. Satellite communication would continue in some areas, but ground equipment would still require electricity and maintenance. Emergency information would need to travel through several different systems because no single network could be assumed to remain reliable. Road transport would slow or stop under heavy ashfall. Fine particles reduce visibility and can make road surfaces slippery, particularly when wet. Vehicle engines draw air through filters that can clog quickly. Ash enters moving parts, scratches windscreens, contaminates oil, and damages electronics. Even ash deposits around 1 mm thick can seriously affect roads and railways by reducing visibility and traction. Restoring transport requires repeated cleaning because wind and traffic can move the material back onto cleared surfaces. Emergency vehicles would face the same conditions as everyone else. Ambulances and fire engines are not fitted with a special exemption from abrasive particles. Rail networks might initially seem more dependable, but ash can interfere with switches, signalling equipment, engines and electrical connections. Tracks would require inspection, and stations could become unusable. Air travel would be disrupted over a far wider region. Volcanic ash can be difficult to distinguish from ordinary cloud, especially at night. Aircraft entering it may suffer scratched windscreens, damaged instruments, blocked sensors, and erosion of exposed surfaces. Jet engines create a more serious problem. Ash particles can melt inside the hot sections of an engine and then solidify on cooler components, disturbing airflow and potentially causing loss of thrust. This has happened during past eruptions, including incidents in which aircraft temporarily lost power from all engines before crews managed to restart them. A super eruption could close large sections of airspace for extended periods. Flights would be cancelled or rerouted, airports would require repeated cleaning, and aircraft already outside the affected area would struggle to move passengers and cargo around the closures. The problem would not be limited to holidays and business trips. Modern supply chains use air freight for medicines, electronic components, specialist equipment, and food with short storage lives. A major aviation shutdown would create delays far beyond the region receiving the heaviest ash. Ships would avoid dense ash clouds where possible. Ash can reduce visibility, clog filters, contaminate machinery, and block water intakes. Ports receiving ashfall would have to clean loading equipment and navigation systems while coping with disrupted roads and railways inland. Agriculture would experience both immediate and longer-term damage. Thick ash can bury crops, break branches, and flatten plants. Finer deposits coat leaves and reduce photosynthesis. Grazing animals may lose access to grass and clean water. Ash can damage teeth and digestive systems if animals consume it with food. The result would depend on the season, crop type, ash thickness, rainfall, and chemical composition. A field covered shortly before harvest could be lost. The same deposit on empty winter ground might create fewer immediate losses, though soil and drainage problems would remain. Acidic compounds associated with volcanic gases can affect vegetation and water. Ash may also contain fluorine and other substances that can harm livestock under some conditions. Farmers would need testing rather than relying on appearance, because a grey field does not provide a useful chemical analysis. Ashfall can alter soil acidity, nutrients, water movement, and root conditions. Heavy deposits may make farmland unusable until material is removed or mixed into the soil. USGS impact studies show that ash can cause crop failure through burial, weight, broken stems, reduced photosynthesis, and changes in soil chemistry. Volcanic material can eventually create fertile soils, which is one reason people farm near many volcanoes. Eventually is doing important work in that sentence. Fresh ash is not instant fertilizer. Soil formation requires weathering organic material, water, microbes, and time. A farmer whose crops have just disappeared beneath 20 centimeters of ash is unlikely to be comforted by the possibility that conditions may improve for somebody several generations later. Food production outside the ashfall area could also be affected through climate changes, transport problems, shortages of fertilizer and fuel, market disruption, and increased demand from regions that lost harvests. The climate effects would come mainly from sulfur gases reaching the stratosphere, not from the ash darkening the sky near the ground. Ash particles generally fall out of the atmosphere relatively quickly. Sulfur dioxide can react with water to form tiny sulfate droplets. When these aerosols remain high in the stratosphere, they reflect part of the incoming sunlight and alter the balance of energy reaching Earth's surface. After the 1991 eruption of Mount Pinatubo, sulfate aerosols helped lower global average temperatures by around 0.5 degrees Celsius for roughly 2 years. A super eruption could inject much more material, but the relationship between eruption size and climate cooling is not simple. The amount of sulfur in magma varies. Some large eruptions release less sulfur than might be expected from their volume, while smaller eruptions can be unusually sulfur-rich. the height and location of the injection matter. Atmospheric circulation distributes aerosols differently, depending on latitude and season. Particle size matters too. Small sulfate droplets are effective at scattering sunlight, but particles can collide and grow. Larger particles fall from the stratosphere faster and may be less efficient at producing prolonged cooling. This creates major uncertainty in estimates of a volcanic winter after a supereruption. Some older simulations produce dramatic global cooling lasting for years. More recent NASA-led modelling, published in 2024, suggested that even very large supereruptions might produce global average cooling of no more than about 1.5 degrees Celsius, partly because larger aerosol particles would limit the cooling effect. The researchers also emphasised that aerosol size remains uncertain and that further model comparisons are needed. A global average change of 1 or 1.5 degrees may sound modest, especially in a room where someone adjusts the thermostat by more than that without consulting anyone else. Global averages hide regional and seasonal extremes. Some areas could experience much greater cooling. Rainfall patterns might shift. Monsoons could weaken or move. Growing seasons could shorten. Frost might occur at damaging times. Other regions could see smaller effects or different combinations of temperature and precipitation. The eruption would also arrive in a climate already influenced by human-caused warming. Volcanic cooling would temporarily mask some warming rather than permanently reverse it. Once the sulfate aerosols settled out, their cooling effect would fade, while carbon dioxide already in the atmosphere would remain. Volcanoes release carbon dioxide, but even very large eruptions do not provide a practical solution to modern climate change. Human activity emits carbon dioxide continuously, and at a much greater annual rate than the world's volcanoes. The main short-term climate influence of a major explosive eruption would be sulfate-driven cooling, not long-lasting greenhouse warming. The most serious global consequence might therefore be food insecurity, rather than a planet permanently locked in ice. Modern agriculture depends on predictable seasons, transport, fuel, machinery, fertilizer, irrigation, electricity, finance, and international trade. A large harvest failure in one region can be balanced by imports from another. Simultaneous poor harvests across several major growing regions would be much harder to manage. Governments might restrict exports to protect domestic supplies. Prices would rise. Wealthier countries and individuals would compete more successfully for available food, while poorer communities would face shortages first. A supereruption would not affect every place equally. Communities near the volcano would face direct destruction. Regions under thick ash would struggle with infrastructure and agriculture. Areas far away might experience price increases, travel disruption, altered weather, and economic recession without ever seeing ash on the ground. Some countries could remain physically unaffected but become essential suppliers of food, fuel, machinery, medicine, and shelter. Their decisions would influence survival elsewhere. The economic effects would spread through connected systems. Factories cannot operate without parts. Hospitals cannot function indefinitely without deliveries. Farms need diesel, seeds, feed, chemicals, and replacement equipment. Supermarkets depend on warehouses and daily transport. Financial markets respond quickly to uncertainty, sometimes with the steady judgment for which financial markets are famous. Insurance systems could be overwhelmed by claims. Governments would need to support displaced populations and damaged industries while receiving less tax revenue. International lending, debt, and currency markets would come under strain. Tourism would disappear from the directly affected region and decline elsewhere as air travel became difficult. Mining, forestry, manufacturing, and energy production could stop where ash or evacuation made work unsafe. Health effects would extend beyond breathing problems. Power failures threaten people who depend on medical equipment. Water disruption increases the risk of disease. Evacuations interrupt treatment for chronic conditions. Crowded shelters allow infections to spread. Food shortages worsen existing health problems. Stress, bereavement, displacement, and uncertainty create long-term mental health effects. Hospitals near the eruption would need to evacuate before conditions became severe. Those farther away could receive large numbers of patients while managing ash, staffing shortages, and supply interruptions. The number of deaths would depend heavily on warning and preparation. A super eruption in a sparsely populated region after an effective evacuation could cause fewer immediate casualties than a smaller eruption beside a crowded city with little warning. The eruption's size alone would not determine the human outcome. Wildlife would face the same broad hazards as agriculture, but without emergency warehouses or government instructions. Animals near the volcano would be killed by heat, ash, collapsing habitat, and contaminated water. Migrating species might avoid some regions, while animals dependent on local food sources could not. Rivers would be altered by enormous volumes of sediment. Rain falling on loose ash could produce lahars, fast-moving mixtures of water, mud, and volcanic debris. These flows can occur during an eruption and continue for years afterward, whenever heavy rain remobilizes deposits. Lahars follow valleys and river channels, sometimes travelling far beyond the areas affected by pyroclastic currents. They can bury bridges, roads, farms, and towns. Rebuilding a bridge would accomplish little if the river remained filled with unstable ash and another wet season was approaching. Lakes and reservoirs could be blocked by debris or contaminated by ash. Rivers might change course. Flooding could affect places that escaped the initial eruption. The landscape near the caldera would be permanently altered on human timescales. Forests would be removed, valleys filled, drainage systems rearranged, and the central region lowered by collapse. New hot springs, vents, lakes, and unstable ground could appear after the main eruption. Activity might continue for years. Smaller explosions, gas emissions, earthquakes, landslides, and lava eruptions could follow. The word eruption can make the event sound as though it has a clear beginning and ending, like a performance followed by everyone collecting their coats. Large volcanic crises can have long tails. Ash would continue moving. Rivers would carry sediment. Infrastructure would fail in stages. Crops would require several seasons to recover. Displaced communities might never return to the same locations. A caldera-forming eruption would not destroy Earth. It would not split the planet open, ignite the atmosphere, or cause every volcano to erupt at once. Those ideas belong to disaster fiction rather than volcanology. It would not automatically cause human extinction either. Humans live on every continent, produce food in many climates, store knowledge in many places, and have communication and transport systems unavailable to earlier societies. Even a severe global disaster would leave large regions outside the direct hazard zone. Survival as a species, however, is a very low standard. The more useful question is how many people could remain safe, fed, healthy, and connected through the years of disruption that followed. The difference between a terrible disaster and a much greater one would depend on decisions made before the eruption reached its largest stage. Monitoring would determine how much warning existed. Evacuation plans would determine how quickly people moved. Food reserves, energy systems, international agreements, medical planning and communication would determine how well communities handled the wider effects. A super eruption would be a geological event, but much of its human damage would come through ordinary systems failing together. Electricity fails, so pumps stop. Pumps stop, so clean water becomes scarce. Roads close, so fuel and medicine do not arrive. Farms lose fuel, so food production falls. Communication breaks down, so people act on rumours. Each problem increases the pressure on the next. That chain can also work in the opposite direction. Backup power keeps water moving. Clear communication reduces panic. Stored food creates time for damaged farms to recover. International transport routes shift around closed regions. Hospitals disperse patients before ash arrives. No plan could make a super eruption harmless. Preparation could prevent many secondary failures from becoming worse than the eruption itself. The first step would be accepting that survival would not depend on an imaginary machine capable of plugging the volcano. It would depend on monitoring early decisions, strong infrastructure, stored essentials, public trust, and cooperation across borders, which moves the question away from what the eruption would destroy and toward how humanity could prepare for an event too large for any one city or country to manage alone. Preparation would have to begin long before anyone knew that a particular super eruption was approaching. Once a large caldera entered severe unrest, there would still be important decisions to make, but that would be a difficult time to discover that evacuation routes were too narrow. Emergency radios had no batteries, or the National Grain Reserve was mainly an impressive collection of empty buildings. The first stage would be accepting what could and could not be controlled. Humanity cannot currently prevent a super eruption. There is no tested method for cooling a continental magma system, releasing its pressure safely, or persuading it to remain underground through a carefully worded letter. Drilling into the magma would not provide a useful pressure valve. A large volcanic system is not a sealed boiler with one convenient plug. It may contain many pockets of melt, crystal-rich material, gas, hot rock, and hydrothermal fluids spread across a wide region. Drilling could be dangerous, technically difficult, and far too small in scale to control the system. A super eruption would involve forces and volumes beyond any engineering project humans have attempted. Preparation would therefore focus on keeping people away from the most dangerous areas, protecting essential services, maintaining food and water supplies, and preserving enough social organisation to manage a long recovery. That may sound less exciting than a machine designed to stop a volcano, but it has the advantage of being possible. The most important tool would remain early warning. Seismic stations, satellite radar, gas sensors, ground instruments, thermal cameras, and field surveys would need to operate continuously at large volcanic systems. Equipment would require backup power, protected communication links, spare parts, and teams able to interpret the measurements around the clock. Monitoring a volcano is useful only if the information reaches the right people quickly. Scientists would need direct communication with emergency agencies, local governments, transport authorities, hospitals, utility companies, farmers, military planners, and national leaders. Warning messages would have to be prepared before the crisis, so that officials were not inventing phrases while the ground moved beneath the office. The US Geological Survey advises emergency managers to treat a volcanic crisis as an extended period that may begin with early unrest and continue for months or years after an eruption. It recommends linking hazard mitigation, warnings, public information, response, and recovery, rather than treating the eruption as one isolated moment. This would be especially important during the uncertain early phase. Scientists might know that magma was moving without knowing how large the eruption would become. Officials would need plans that could expand as the threat changed. A small zone might be closed first. Nearby communities could then be evacuated. Aircraft routes could be altered. Hospitals might begin transferring patients. Food, fuel, masks, and medical supplies could be moved into areas expected to receive displaced residents. If the warning signs continued to intensify, the operation would grow. Trains, buses, private vehicles, and possibly aircraft would move people away from the highest risk region. Traffic would need to travel mainly outward, which sounds obvious until thousands of people attempt to drive home first to collect a laptop charger and a houseplant. Evacuation plans would have to identify who needs assistance: older adults, hospital patients, care home residents, prisoners, school children, people without cars, and those with disabilities cannot simply be told to leave and wish the best of luck. Pets and livestock would also matter. People sometimes delay evacuation because they will not abandon animals. A plan that ignores this behaviour is not realistic, however tidy it may look in a folder. Routes would need alternatives because earthquakes could damage bridges and roads before the eruption. Ash could make driving unsafe. Fuel stations might lose electricity. A route passing through a river valley could later become exposed to lahars. Regular exercises would reveal these problems while there was still time to fix them. UN disaster guidance defines preparedness as the knowledge and capacity developed before an emergency, including contingency plans, stockpiled supplies, evacuation arrangements, public information, training, and field exercises. It also stresses that plans should be based on actual risk and supported by institutions, law, and budgets. The budget is less dramatic than the evacuation, but it determines whether the evacuation works. A beautifully designed plan without trained staff, maintained vehicles, communication equipment, or money is mainly a piece of organised optimism. Close to the caldera, evacuation would be the only reliable protection from pyroclastic currents and major ground collapse. Sheltering inside an ordinary building would not be enough. These areas would have to be emptied before the eruption reached that stage. Farther away, where the main threat was ashfall, officials might tell people to remain indoors. Sending everyone onto roads during heavy ash would create additional danger, strain fuel supplies, and expose more people to poor visibility and engine damage. The correct action would therefore depend on location. One community might need to leave immediately. Another might be safer indoors. A third might prepare to receive evacuees. Clear maps and local instructions would be essential, because the general advice to get away from the volcano becomes less useful when the ash cloud is crossing several countries. Households in ashfall zones could reduce harm with fairly ordinary preparation. They could store water, non-perishable food, medication, eye protection, suitable particulate masks, batteries, lighting, radios, cleaning equipment, and material for sealing gaps around doors and windows. Plans should include an out-of-area contact and a meeting place, in case family members are separated. USGS guidance also advises knowing local hazard zones, evacuation routes, and school or workplace plans before unrest begins. A basic kit would not carry a family through years of global disruption. It would help them manage the first days, when shops might be closed, water systems uncertain, and emergency services occupied elsewhere. During ashfall, keeping ash out of buildings and machinery would become a constant task. Windows and doors would need to remain closed. Sensitive electronics could be covered. Ventilation systems might require special filters or temporary shutdowns. Vehicles should be used only when necessary, because ash can clog filters and damage engines. People working outdoors would need respiratory and eye protection. Anyone with asthma, chronic lung disease, or other respiratory problems would require extra care and reliable access to medication. The World Health Organization notes that volcanic eruptions can cause respiratory illness, eye and skin irritation, burns, injuries, and contamination of food and water, while also disrupting transport, communication, and health services. Masks would not solve every problem. They can reduce inhalation of fine particles when correctly selected and fitted, but they do not protect against every volcanic gas or make it safe to enter areas threatened by pyroclastic currents. A mask is useful equipment, not a small fabric force field. Public advice would need to explain such distinctions repeatedly. During emergencies, people often receive a mixture of official instructions, rumours, old photographs, unrelated videos, and messages from a cousin who has recently become very confident about geology. Communication systems would need several layers: mobile networks, radio, television, satellite links, public sirens, community organisations, and door-to-door teams could all play a role. Messages should be short, specific, and honest about uncertainty. Officials would have to say what is known, what remains unclear, what action is required, and when the next update will arrive. Silence allows rumours to fill the gap. Overconfidence creates another problem if later events do not match the original statement. Trust built before the crisis would become one of the most valuable forms of preparation. Communities are more likely to follow instructions when local officials, scientists, and emergency agencies have communicated clearly during quieter periods. That means discussing uncertainty without turning every earthquake swarm into a rehearsal for the end of civilization. It also means explaining that a falling alert level does not prove the earlier warning was false. Magma can move, create real danger, and then stop. Hospitals would need plans for both evacuation and continued operation. Facilities close to the volcano might transfer patients early, before roads became crowded. Hospitals farther away would prepare for burns, injuries, respiratory illness, stress-related conditions, and interruptions in ordinary care. Backup generators would require fuel, protected air intakes, and maintenance. A generator that inhales volcanic ash may become an expensive metal cupboard at precisely the wrong moment. Medical oxygen, medicines, sterile equipment, dialysis supplies, blood products, and protective equipment would need to be distributed across several locations. Central warehouses are efficient during normal life, but vulnerable when one transport corridor closes. Health systems would also need to continue routine services. Babies would still be born, people would still require insulin, cancer treatment, antibiotics, mental health care, and emergency surgery. WHO guidance treats emergency preparedness as a property of the whole health system, rather than a temporary activity added after a crisis begins. Water might become the most urgent resource after immediate evacuation. Reservoirs and treatment plants could receive ash. Pipes might survive while pumps lost power. Filters could clog more rapidly than replacement parts arrived. Communities dependent on rainwater collection would have to disconnect tanks before ashfall or find alternative supplies. Preparation would involve protecting water intakes, stockpiling treatment chemicals and filters, installing backup electricity, identifying emergency wells, and arranging water transport. Wastewater plants would need separate plans because ash washed into drains can damage equipment and reduce capacity. Household water storage would provide a short buffer, but large urban populations require functioning systems. A city cannot rely for long on everyone owning several bottles in a cupboard. Electricity networks would need to be divided into sections so that one damaged area did not bring down the entire system. Utilities could protect substations, maintain spare transformers and insulators, clear ash from equipment, and identify which services must receive power first. Hospitals, water plants, communication centres, food warehouses, fuel depots, and emergency shelters would take priority. Some factories and commercial districts might be shut down deliberately to preserve limited generation capacity. Resilient infrastructure is not simply stronger concrete. It includes redundancy, repair capacity, alternative routes, trained staff, and systems that continue providing essential services when one component fails. UNDRR guidance places energy, transport, water, wastewater, waste management, and digital communication among the critical services that must be planned together rather than separately. That connection matters because infrastructure failures rarely remain alone. Without electricity, fuel pumps may not work. Without fuel, repair vehicles stop. Without communications, crews do not know where to go. Without clean water, shelters become health hazards. The aim would be to interrupt these chains before one failure multiplied into several. Ash removal would become a major public operation. Cities would need equipment, protective clothing, disposal sites, traffic plans, and agreements for help from neighbouring regions. Ash should not simply be pushed into drains or rivers. Disposal sites would have to avoid contaminating water and prevent dry material from blowing back into populated areas. Some deposits could be stabilised with soil, gravel, vegetation, or controlled moisture. Cleaning would need priorities. Hospital entrances, power facilities, water plants, main roads, airport surfaces and vulnerable roofs would be cleared before decorative fountains received attention. Businesses would need spare air filters, oil filters, sealed storage, replacement electronics, and procedures for shutting down equipment. USGS planning guidance recommends identifying which facilities must remain operational, protecting vulnerable machinery, preparing communication plans, and arranging equipment and disposal locations before ash arrives. Improvised cleanup could create additional harm. Dry sweeping sends fine ash back into the air. Too much water turns it into a heavy paste and places more weight on roofs. People climbing onto ash-covered roofs can fall, particularly when the surface is wet. Official instructions would need to reflect local building types, ash thickness, and weather. A method suitable for a small dry deposit might be dangerous under deep wet ash. Food would create the longest and most difficult problem. Countries already maintain different forms of strategic food storage, but a severe global volcanic event could require reserves large enough to cover poor harvests across several seasons. Grain, pulses, cooking oil, infant formula, animal feed, fertilizer, seeds, and fuel would all matter. Storage alone is not enough. Food must be inspected, rotated, protected from pests, and distributed before it spoils. Warehouses need electricity, workers, vehicles, security, and accurate records. A reserve that cannot leave the warehouse is an unusual form of interior decoration. Governments could spread stocks across multiple regions, rather than concentrating them near one port or capital. Agreements could identify transport routes that remain useful if air travel is restricted. Railways, ships, and inland waterways might carry much of the burden. Emergency planners would also need to protect ordinary food markets. If governments purchased every available product at once, they could create the shortages they were trying to prevent. Price controls, rationing, cash support, public distribution, and restrictions on hoarding might all be considered depending on the severity of the crisis. FAO guidance recommends food system monitoring, early warning, emergency food and financial reserves, protection of productive assets, and rapid restoration of local production and market access after disasters. It also emphasises plans for vulnerable and displaced populations rather than assuming that food will reach everyone through ordinary commerce. Agricultural preparation could include maintaining crop varieties suited to cooler temperatures, shorter growing seasons, lower light, and altered rainfall. Farmers might change planting dates, use protected growing structures, or shift toward crops that mature quickly. No universal emergency crop would work everywhere. Soil, temperature, water, machinery, diet, and local knowledge all matter. A plant that performs well in one country may fail completely in another. Greenhouses and indoor farms could protect some production from ash and weather, but they require energy, clean water, materials, nutrients, and maintenance. They could help supply vegetables, seedlings, and specialized foods. They would not quickly replace the enormous fields that produce most of the world's wheat, rice, maize, and soy. Research into alternative foods could offer another layer of preparation. Microbial protein, algae, fungi, and foods produced from agricultural or industrial byproducts might reduce pressure on ordinary farmland during a severe shortage. These systems would need to be tested, regulated, powered, and built before an emergency. A clever laboratory process is not the same as a global food industry. Factories, supply chains, trained workers, and public acceptance take time. Seed banks would support recovery by preserving crop diversity. The Svalbard Global Seed Vault stores duplicate samples from gene banks around the world as a backup in case original collections are lost through disasters, conflict, policy changes, or other failures. Its purpose is to preserve genetic resources for agriculture, not to serve as an emergency supermarket containing enough grain to feed the population. The distinction is important. A small packet of rare wheat seeds might help breeders restore a useful variety. It will not provide dinner for a city. Working gene banks, seed producers, plant breeders, farmers and distribution networks would all be needed to turn preserved seeds into large harvests. Protecting those institutions matters as much as protecting the vault itself. Livestock systems would require feed reserves, clean water, veterinary medicine, shelter from ash, and plans for relocation. In severely affected regions, maintaining every herd might be impossible. Governments could have to decide which breeding animals and genetic lines to protect while reducing the number of animals competing for scarce feed. Fishing could help some countries replace lost crops, but oceans are not an unlimited emergency cupboard. Ports, fuel, refrigeration, and transport would still be required, and sudden overfishing would damage future supplies. International trade would therefore remain essential. One region might have food but lack fuel. Another might produce medicine but need grain. A third could offer ships, engineers, or water treatment equipment. Pre-arranged agreements would make cooperation easier. Countries could decide how emergency exports, shipping priorities, customs rules, and financial support would operate before shortages encouraged everyone to become less generous. The World Food Programme manages a network of humanitarian response depots that pre-position medical kits, shelter equipment, ready-to-use food, and logistic supplies at hubs in several regions. A super eruption would exceed the normal scale of this network, but the underlying principle would remain useful. Supplies already positioned around the world can move faster than supplies ordered after roads and airports begin closing. Survival would depend heavily on fairness. Wealthy countries could purchase scarce food and equipment at prices poorer countries could not match. Within each country, wealthy households could stockpile supplies, while low-income families struggled with rising costs. Without deliberate protection, the people least responsible for the disaster would experience its worst effects. Food distribution, shelters, healthcare, transport, and financial assistance would need to include people without identification documents, bank accounts, permanent housing, or political influence. Displaced populations might remain away from home for years. Temporary shelters would have to become functioning communities with schools, clinics, sanitation, employment, and safe housing. A row of tents may work for the first nights. It is not a reasonable urban plan for the next decade. Mental health support would also matter. People could lose homes, relatives, livelihoods, familiar landscapes, and confidence in the future. Children might spend years away from their communities. Farmers could watch land used by generations of their family disappear beneath ash. Practical assistance reduces psychological harm. Reliable housing, food, communication, schooling, and information give people more control than occasional advice to remain positive while standing in a queue for bottled water. Preserving knowledge would be easier than preserving comfort. Scientific records, medical information, engineering plans, agricultural instructions, and cultural archives already exist in many places and formats. Distributed digital and physical backups could protect them against regional loss. Education would continue during recovery because reconstruction requires skilled people. Engineers, electricians, nurses, mechanics, farmers, builders, teachers, and water specialists would be more immediately useful than a large committee devoted to naming the disaster. None of these preparations would be designed only for a super eruption. Stronger hospitals, diversified food supplies, backup power, protected water systems, emergency communication, and well-practiced evacuations also help during earthquakes, floods, storms, pandemics, conflict, and ordinary volcanic eruptions. That is one reason preparation for a very rare event can still be sensible. The same investment can reduce many more common risks. There would be limits. No country could maintain every service at normal levels through a major global disruption. Choices would be necessary. Some industries would pause, consumption would change, travel would become restricted, governments might ration fuel and food. The aim would not be to preserve everyday life exactly as it was. It would be to keep the essential parts working while the atmosphere cleared, agriculture adjusted, and damaged regions began recovering. Humanity would probably survive a super eruption. That does not mean survival would be automatic or evenly shared. The outcome would depend on where the eruption occurred, how much warning appeared, how governments responded, and whether countries cooperated when supplies became scarce. Technology would help, but organisation would matter just as much. A satellite can identify an ash cloud. It cannot persuade people to trust an evacuation order. A warehouse can contain grain. It cannot guarantee fair distribution. A backup generator can power a hospital only if someone maintained it and remembered where the fuel was stored. Preparation is mostly the unglamorous work of making sure that ordinary systems continue under extraordinary pressure. It would also require proportion. Building resilience does not mean living in daily fear of a supervolcano. There is no evidence that one is currently approaching. Emptying supermarket shelves whenever Yellowstone experiences an earthquake swarm would create more immediate problems than the volcano. The useful response is steady rather than panicked. Monitor the large calderas, improve warning systems, strengthen infrastructure, practice evacuations, protect food diversity, distribute emergency supplies, and plan for recovery. After that, there is no button to press and no date to circle. There is only the long interval in which humans continue living above a geologically active planet, aware that enormous eruptions are possible, but also aware that possibility is not the same as arrival. Understanding that wait may be the hardest form of preparation, because it asks us to take a rare hazard seriously without treating every quiet year as borrowed time and every small earthquake as the beginning of a countdown. That countdown is the wrong way to think about the long wait. A supervolcano is not moving steadily toward an appointment with us. There is no hidden display beneath the crust showing several thousand years, several hundred years, 3 weeks, and then an urgent suggestion to leave the area. Volcanic systems change unevenly. They receive new magma, lose heat, fracture, seal themselves, release gas, and shift pressure through rock and water. Some remain active for millions of years. Some produce several large eruptions and then gradually fade. Others continue releasing heat long after their last magma reached the surface. The absence of a countdown can feel unsatisfying because people are comfortable with schedules. We plan journeys, meals, meetings, birthdays, and alarm clocks. Even events far beyond our control are easier to discuss when they have dates attached. Astronomers can calculate an eclipse many years in advance. Engineers can estimate when a spacecraft will arrive at another planet. We know when winter will begin, even if the weather occasionally treats the season as a loose recommendation. A super eruption does not offer that kind of regularity. Its timing depends on the internal condition of a changing geological system that is mostly hidden from view. Scientists can observe the effects of those changes, but they cannot calculate the next giant eruption using orbital mechanics or a repeating calendar. This leaves us with a wide range of possible waiting times. The next super eruption could occur somewhere on Earth within the next few thousand years. It could happen much farther into the future. No known volcanic system is currently showing evidence that an event of that scale is approaching, and there is no reliable way to identify the next one while all the likely candidates remain in their present conditions. The answer is therefore not that we have 10,000 years left, or 50,000, or 100,000. Those numbers may appear in discussions of average recurrence, but averages are not deadlines. If several super eruptions occur during a million-year period, dividing the time by the number of events would produce an average interval. That can help describe how rare the events have been across geological history. It cannot tell us where the next one will happen, or how far away it is. Imagine a quiet road where 5 buses pass during one afternoon. You could calculate an average interval between them. That does not prove another bus will arrive at the exact expected minute. Particularly if each bus came from a different route, the timetable is missing, and one of them may not have been a bus at all. The geological record creates similar difficulties, although it contains more ash and fewer useful signs. Some ancient super-eruption deposits have been identified and dated. Others may be hidden beneath younger rock, ocean sediment, ice, vegetation, or entire landscapes altered by erosion. The number of known events is probably not the complete number that occurred. Even if the record were complete, super-eruptions do not appear to follow a global rhythm. They are produced by separate volcanic systems responding to regional tectonic and magmatic conditions. One eruption does not make another more likely, simply because a worldwide average has reached a certain value. Earth has not become overdue. The idea that it as often comes from treating probability as a form of memory. If a rare event has not happened for a long time, people may feel that its chance must be increasing. This can be true for some physical systems, particularly when stress or damage accumulates in a measurable way. It is not automatically true for every rare event. When a fair coin lands on heads several times, tails does not become more likely on the next throw. The coin does not become embarrassed and attempt to restore balance. A volcanic system is more complicated than a coin because its internal state changes. Its probability may rise when magma accumulates and unrest develops. It may fall when the system cools or pressure is released. The passage of time alone does not tell us which change has occurred. That is why modern measurements matter more than a simple count of years since the last eruption. If a caldera begins producing rapidly increasing earthquakes, widespread deformation, changing gas emissions, and evidence of moving magma, scientists will not dismiss those signs because the average interval suggests the eruption should still be far away. The reverse is also true. They will not declare an eruption imminent merely because a large number of years has passed, while monitoring remains at ordinary background levels. This can make volcanic risk sound contradictory. A super eruption is possible, but not expected soon. The consequences could be severe, but the annual probability is extremely low. Preparation is useful, but panic is not. All three statements can be true at the same time. People deal with low probability risks every day. Buildings are designed with fire exits even though most never burn. Bridges are built to withstand forces they may never experience. Hospitals maintain plans for events they hope will not occur. The existence of a plan does not mean a disaster is expected tomorrow. It means the consequences justify preparation even when the event is unlikely. Super eruption planning works best when it strengthens systems that are useful for many emergencies. Better monitoring helps during smaller volcanic eruptions. Food reserves help during poor harvests, wars, supply chain failures, and severe weather. Backup power protects hospitals during storms and earthquakes. Clear public communication is useful whenever rumours begin moving faster than evidence. A society prepared for several overlapping problems would also be better placed to handle a large volcanic crisis. This is more practical than constructing a civilization around one extreme scenario. It would make little sense to direct every available resource toward a super eruption while neglecting floods, fires, ordinary volcanic hazards, disease, and failing infrastructure that affect people much more often. Risk is partly about severity and partly about probability. An event capable of enormous damage deserves study. An event happening regularly deserves attention too, even if it lacks an alarming name. For most people living today, the direct risk from a super eruption is extremely small. Many people face greater danger from earthquakes, storms, heat, traffic, air pollution, and illnesses that arrive without documentaries describing them as planet killers. That comparison should not be used to ignore volcanoes. It helps place them in proportion. The nearest active volcanic system may matter more than the nearest supervolcano. A moderate eruption can destroy homes, close airports, contaminate water, and displace communities. It does not need to cross the VEI 8 threshold to become the most important event in someone's life. Residents near Campi Flegrei are concerned about earthquakes, uplift, buildings, evacuation routes, and the possibility of a future eruption. Their immediate decisions do not depend on whether that eruption would qualify as a super eruption. People around Sakurajima regularly manage ash from a volcano erupting within a larger caldera. Communities near Popocatépetl, Merapi, Etna, Mayon, and many other active volcanoes deal with hazards that are far more frequent than a caldera-forming event. The quiet wait for a super eruption happens alongside ordinary volcanic activity across the planet. At any moment, Several volcanoes may be releasing gas, producing small explosions, sending out lava, or showing unrest. Most of these events receive little international attention unless they threaten a city or interrupt flights. This creates a distorted picture. People may know the name Yellowstone while knowing very little about volcanoes that have erupted repeatedly during their lifetime. Yellowstone is interesting because of its geological history, its hydrothermal features, and the scale of its ancient eruptions. It is not a machine that exists only to produce the next global disaster. Visitors see geysers, hot springs, lakes, forests, wildlife, rivers, and mountains shaped by several geological processes. The volcanic system contributes heat and structure to the region, but most of what happens there on an ordinary day is not a warning. The ground may experience small earthquakes that nobody feels. A section of the caldera may move by a few millimeters. Hot water circulates beneath a thermal basin. A bison ignores a sign explaining where visitors should stand. Scientists record the changes, compare them with previous years, and continue watching. That ordinary monitoring is what the long wait looks like in practice. It is not a room filled with people staring at one red light. It is a continuing program of measurements, field work, equipment repairs, data analysis, and cautious updates. A seismic station may record thousands of signals, most of which represent background earthquakes, weather, machinery, animals, or other harmless sources. Analysts identify patterns that deserve closer study. Satellite images are compared over months and years. Gas samples are collected from the same locations. Springs are measured, rocks are mapped. Computer models are revised as new evidence changes the picture. Most days do not produce dramatic results. That is not wasted work. A reliable warning depends on knowing what normal activity looks like. Without years of background measurements, a sudden change is harder to recognize. The quiet record gives meaning to the unusual signal. The same principle applies to public understanding. People who learn about volcanic systems only during a crisis may struggle to interpret uncertainty. They may assume that any earthquake means eruption, or that an unsuccessful forecast proves the danger was invented. Regular communication during quiet periods can explain how alert levels work, why unrest sometimes ends without eruption, and why officials may act before every question has been answered. The long wait should be used for education rather than fear. Schools in volcanic regions can teach local hazards and evacuation routes. Communities can practice moving vulnerable residents. Utility companies can identify equipment exposed to ash. Farmers can plan for livestock and water protection. Hospitals can test backup systems. None of these activities requires anyone to believe that a super eruption is close. They simply recognize that geological hazards exist and that calm preparation works better than hurried improvisation. Scientific research also benefits from time. Every ordinary eruption provides information about magma movement, gas release, ash transport, and emergency response. Improved satellite systems detect smaller changes. Faster computers allow more detailed simulations. Laboratory experiments reveal how crystals and melts behave under high temperature and pressure. Future researchers will probably understand caldera systems better than we do now. They may develop more accurate ways to estimate melt concentration. They may detect chemical changes at greater depth. They may combine seismic, deformation, and gas data into forecasts that update continuously. Even then, perfect prediction is unlikely. A natural system can be understood well without becoming completely predictable. Weather science has advanced enormously, yet the atmosphere still produces surprises. Earthquake science can identify dangerous faults without naming the exact hour of the next rupture. Volcanology may reach a point where major unrest gives months of useful warning, and the likely eruption scenarios are described with much greater confidence. It may never provide an exact date years in advance. That would still be a major success. The purpose of forecasting is not to satisfy curiosity with a perfect number. It is to provide enough information for safer decisions. If a population leaves before pyroclastic currents arrive, the forecast was useful, even if the eruption began several hours later than expected. If aircraft avoid an ash cloud, the warning worked even if the cloud travelled in a slightly different direction. Science does not need to predict every detail to reduce harm. There is also no reason to assume that humanity will remain unchanged throughout the wait. If the next super eruption is tens of thousands of years away, the societies facing it may have technologies, political systems, and settlement patterns very different from ours. Cities may occupy different regions, agriculture may use different crops and methods, energy systems may be more distributed, space-based observation may provide continuous imaging of every active volcanic field. Or people may still be arguing over whether a small earthquake beneath Yellowstone means everyone should purchase 12 years of canned beans. Long timescales invite speculation, but they also make present-day certainty impossible. We do not know whether the next super eruption will affect our civilization, a distant future civilization, or a human population change beyond easy recognition. The only population we can prepare is the one that exists now. This is why the question, how long until the next supervolcano erupts, eventually becomes less useful than several smaller questions. What are the volcanoes doing now? Are their monitoring systems adequate? Do nearby communities understand the hazards? Can governments communicate clearly during unrest? Are food, water, power and transport systems resilient? Those questions have answers that can be improved. The first one is answered daily by observatories. At present, no large caldera is known to be preparing for a super eruption. That statement may change one day. It may not change for many generations. Until then, the sensible position is attention without alarm. We can recognize that Earth produces rare, immense eruptions. The deposits are real. Calderas exist because these events happened. Ash from ancient eruptions is preserved across continents and ocean floors. We can also recognize that our planet spends almost all its time not producing them. Forests grow inside calderas, lakes fill collapsed basins, animals cross old lava flows, cities develop beside volcanic fields, generations live entire lives above warm crust without witnessing a major eruption. A landscape created by catastrophe does not remain catastrophic every day afterward. This is easy to forget when geology is compressed into a documentary. Millions of years become a few minutes. Eruptions follow one another before the viewer has finished a cup of tea. The empty periods disappear because very little seems to happen during them. For the planet, those quiet intervals are most of the story. Yellowstone's last caldera-forming eruption occurred hundreds of thousands of years ago. Since then, glaciers advanced and retreated. Species migrated. Rivers changed course. Humans spread across continents, developed agriculture, built cities, and eventually installed cameras beside geysers. The volcano's timescale has continued through every human event without adjusting itself to our calendar. Looking at the night sky can make that scale slightly easier to understand. The stars appear steady during one evening, but they are not fixed. They move, age, and change over periods much longer than a person can observe directly. The same is true beneath the ground. Rock that appears solid and permanent is part of a slow system of heat, pressure, melting, uplift, erosion, and tectonic movement. Neither the stars nor the crust are truly still. They simply change at rates that do not always fit human attention. A quiet caldera is not necessarily dead. An active caldera is not necessarily close to eruption. These are different states within processes that extend far beyond one lifetime. The long wait is therefore not a pause before an inevitable event at a known location. It is the normal condition of living on an active planet. Earth has always contained risks. Continents move, oceans circulate, storms form, rivers flood, mountains rise and wear down. Volcanoes build land and destroy it. Life continues not because the planet is harmless, but because most places are habitable most of the time, and living things adapt to changing conditions. Humans have added something unusual to that process: the ability to investigate dangers before they arrive. We can identify old ash layers, date crystals, measure ground movement from space, and detect earthquakes smaller than a passing vehicle. We can model an eruption that has not happened and design plans for people not yet in danger. Those abilities do not give us control over the volcano, they give us options. We can choose where to build critical facilities, we can protect water systems, we can maintain food reserves, we can prepare evacuation routes, we can decide not to turn an unverified rumour into a public emergency. The final option may be among the most frequently required. Whenever Yellowstone produces an earthquake swarm, online claims appear announcing that the volcano is waking. Photographs of dead animals, damaged roads, or unusual clouds may be presented without context. Old videos return with new dates attached. Most of these claims can be checked against observatory reports. Official monitoring agencies publish earthquake information, ground deformation, gas measurements, and alert levels. A genuine movement toward a large eruption would not depend on one secret photograph or one person noticing that a geyser seemed unusually enthusiastic. It would produce widespread evidence across several monitoring systems. Multiple scientific organizations would see it. Governments would respond. Airspace and roads would be managed. The information would not remain hidden in a social media post between a recipe and an advertisement for garden furniture. This does not mean institutions never make mistakes. It means an extraordinary claim should be supported by more than a dramatic tone. Calm skepticism is another form of preparedness. For tonight, the ground beneath the known large calderas continues its ordinary activity. Heat moves through rock. Water circulates. Small earthquakes occur. Instruments record data. Researchers examine it. Somewhere beneath one of these systems, magma may be cooling. Elsewhere, new magma may be rising slowly from greater depth without creating an eruption. Many changes will stop before reaching the surface. Across the night side of Earth, people are sleeping above faults, old lava, sediment, granite, and ancient volcanic deposits. Most will wake without noticing anything geological at all. Perhaps you are one of them. You may be listening from a city built on ordinary crust, from an island formed by volcanoes, or from a region where an ancient caldera sits quietly beneath forests and roads. The local geology may be more complicated than the view from your window suggests. That complexity does not require fear. It is simply part of where we live. So, where are you listening from tonight? Is there an active volcano in your country, or an old one hidden somewhere nearby? And has the ground beneath your home been quiet for thousands of years, or merely quiet for today? If you have enjoyed this slow journey through calderas, ash clouds, magma systems, monitoring stations, and the unusually difficult question of when the next super eruption might occur, you are very welcome to like the video and subscribe to Just About Earth. It helps this quiet place reach other people who enjoy learning about enormous geological events in the least alarming way possible. We began by asking how long we have until the next supervolcano erupts. The most accurate answer remains that we do not know. It may be thousands of years. It may be much longer. No scientific evidence shows that one is approaching now. What we do know is that a super eruption would probably produce extensive warning signs, that modern monitoring would detect many of those changes, and that preparation could reduce the harm even if no technology could stop the event itself. The uncertainty is not a reason to remain frightened. It is a reason to keep observing. For now, the calderas remain part of the landscape. The instruments remain on. The stars continue moving above us, and far below, the Earth continues changing at its own pace. There is no countdown to listen for tonight. Only the ordinary sounds around you, the steady air in the room, and a planet that is active, complicated, closely watched, and currently quiet enough for sleep. Sleep well, fellow traveller, wherever on Earth you are.